For years, one number ruled the cosmos. Astronomers looked at the deepest images from space and declared that the observable universe holds about 2 trillion galaxies. It was the kind of number that ends a conversation, big enough to feel infinite, precise enough to feel final. But what happens when that final answer turns out to be just the opening move? Tonight, we're going to step into the moment the universe changed. Again. Because the James Webb Space Telescope is not just sharpening our view of distant galaxies, it is quietly tearing at the edges of that 2 trillion galaxy headline and forcing scientists to ask a much stranger question. Not how many galaxies are there, but what are we even counting? Before we get started, remember how that original estimate was built. Hubble stared at tiny, empty patches of sky for days and weeks, revealing thousands of faint smudges that turned out to be entire galaxies. Scientists then extrapolated, adding in galaxies too dim for Hubble to see. The result? A grand census of the observable universe, a cosmic city with 2 trillion island universes. Expectation: the deeper we look, the more of those ultra-faint galaxies we should find. Reality: Webb is seeing something far more unsettling. At the very edge of time, only a few 100 million years after the Big Bang, this spacecraft is finding galaxies that are too bright, too massive, and too organized for their age. They shine like cosmic skyscrapers in a universe that was supposed to be a village of glowing shacks. Some of these early objects appear to contain as many stars as the Milky Way, packed into a fraction of the volume, existing when the cosmic clock had barely started. No one expects that. No one predicts fully grown galactic giants, while the universe is still in its cosmic infancy. Yet the light is there in Webb's infrared images, streaming across 13 billion years of space, and that is only half the problem. In other directions, Webb seems to find fewer of the ultra-faint galaxies that models demanded to reach 2 trillion. Instead, it hints at something else: missing light, obscured by dust, invisible scaffolding of dark matter guiding where galaxies can form, delicate structures that do not show up as neat, countable islands. A hidden layer beneath them, a pattern beneath the old census. By the end of tonight, you're going to understand how that 2 trillion number was discovered, why the standard model of the universe is suddenly under pressure, and what Webb is really seeing at the boundary of the cosmic dawn. Now, let's begin. If 2 trillion galaxies was just the surface, what exactly is hiding underneath, and how deep does this go? To understand what Webb is overturning, you have to rewind to the pre-JWST universe, a time when a handful of tiny images from a single spacecraft seemed to map out almost everything. Before we get started with the surprises, go back to the Hubble Ultra Deep Field. Hubble stared at what looked like an empty patch of space, a region so small that held at arm's length it was about the size of a grain of sand on your fingertip. The original plan is simple. Take a long exposure. Let the light from the faintest galaxies in the cosmos slowly accumulate on the detectors. What appears is not emptiness, but thousands of galaxies packed into one microscopic window on the sky. That image and its even deeper cousin, the Hubble Extreme Deep Field, became core samples of the cosmos. Like drilling a narrow shaft through Antarctic ice to read climate history, scientists used these shafts through space and time to read the history of galaxies. Count how many appear at each brightness. Correct for the ones just below the detection limit. Then scale that census up to the full 4 steradians of the observable universe. The logic is straightforward. The execution is not. To go from a few thousand galaxies in a tiny field to trillions across the sky, Astronomers lean on a model called the galaxy luminosity function. It describes how many galaxies exist at each intrinsic brightness, from giant spirals down to ultra, faint dwarfs. The faint end is crucial because those dim systems are expected to be vastly more numerous than the bright showpieces, but Hubble cannot see most of them directly. So the model has to fill in the darkness, assume a certain slope for the faint population, assume how galaxy brightness evolves with distance and with cosmic time, fold in how dust hides light, how the expansion of space stretches it into the infrared, and how the early universe should be dominated by small, rapidly forming systems. Then integrate that function over all volumes and all epochs. The result, around 2016, is the famous estimate, roughly 2 trillion galaxies within the observable boundary. Not a literal head count, a model, dependent extrapolation from incomplete data, with the largest uncertainties sitting exactly where no telescope had clear vision, the ultra-faint end, and the first few 100 million years after the Big Bang. Yet the number sticks. It's simple. It's awe-inducing. It feels like a final answer. Tonight, we're going to see why that was always a myth. Astronomers knew the caveats. The public mostly heard the headline. And the real universe, it is not obligated to respect a luminosity function drawn from a sand grain of sky. No one expects the earliest galaxies to line up neatly with those extrapolations. No one predicts that when a new spacecraft finally peers into that uncharted regime, it will find a hidden layer that forces the entire model to bend. And right there, the first cracks begin to show. In the last few years, teams went back to those famous Hubble deep fields with new tools and a colder eye. Same images, different conclusions. When the original 2 trillion estimate was made, astronomers had to extrapolate from a tiny patch of space, assuming that the faint smudges Hubble could barely see were just the tip of a vast iceberg of even fainter galaxies. Now, upgraded image processing and sharper models suggest that iceberg may have been exaggerated. The problem is subtle. Hubble's detectors are not perfect windows, they are noisy, aging sensors. Random speckles, cosmic rays, and the solar wind of charged particles all leave their fingerprints. Early on, separating real ultra-faint galaxies from this background was like trying to hear whispers in a crowded room. With better algorithms, more realistic simulations of the instrument, and a deeper understanding of how the detectors misbehave, some of those supposed whispers fade away. A fraction of the faintest galaxies begin to look more like ghosts in the machine. At the same time, galaxy models have evolved. The original extrapolations assumed a smooth distribution. Many more tiny, dim galaxies than big bright ones. But when those assumptions are updated with new physics of star formation, feedback, and dark matter halos, the curve changes. Fewer ultra-faint systems are needed to explain the light Hubble actually saw. The math that once inflated the count now quietly lets air out of the 2 trillion balloon. Then JWST arrives and does something no one expects. It peels back the universe in infrared. Suddenly, regions that were nearly black in Hubble's view light up with structure. Dust-shrouded galaxies appear. Very distant, highly redshifted systems step into focus. Tonight, we're going to follow that pivot because this is where the hidden layer stops behaving the way the model said it should. By the end of tonight, you're going to understand a strange twist. JWST's deeper vision does not simply add millions of new pinpricks to the tally. In some cases, it does the opposite. Light that Hubble recorded as a faint haze, easily interpreted as the blended glow of countless tiny galaxies, is now resolved into fewer, larger, more massive systems. The same flux, redistributed, not a crowded swarm of fireflies, but a smaller number of floodlights. The emerging picture is almost paradoxical. The total number of galaxies in the observable universe may be lower than 2 trillion, perhaps far lower, yet the early cosmos itself looks more crowded, with surprisingly bright objects. At redshifts, where theory expected fragile Galaxies, JWST, has discovered candidates that resemble mature cities of stars. No one predicts skyscrapers in a cosmic stone age, but there they are. So the correction is not just up or down, it is structural. Fewer total galaxies, more massive ones appearing far earlier, and a hidden layer that refuses to match the blueprint. Now, let's begin to ask the unsettling question this crack reveals. If the galaxy census was off, what else about the universe's architecture might be wrong? To test that architecture, you need a witness that can see the universe when it was still under construction. Not just a sharper telescope, a different kind of eye on space. That witness is the James Webb Space Telescope, a spacecraft the size of a tennis court, folded into a rocket fairing, then unfolded 1 million miles from Earth. Its primary mirror is not one piece of glass, but 18 hexagonal segments, gold, coated to grab every stray photon of faint infrared light drifting in from the edge of the observable cosmos. Where does it live? Not in low Earth orbit like Hubble, racing around the planet every 90 minutes. Webb sits out at the Sun-Earth L2 point, about 1.5 million kilometers, or nearly 1 million miles, beyond our world. There, the Sun, Earth and Moon all stay on the same side. So a 5-layer sunshield the size of a tennis court can keep the telescope in permanent night. Cold, dark, sheltered from the solar wind and our planet's heat. That is exactly what those infrared eyes need. Before we get started on what Webb has actually discovered, it helps to understand why infrared is the language of the early universe. As space expands, it stretches the light traveling through it. Wavelengths that left the first galaxies in brilliant ultraviolet and visible hues are dragged outward, red-shifted, until they slip beyond what human eyes and Hubble's optics can see. By the time that light crosses 13 billion years of expanding space, it lives in the infrared. If a telescope cannot see in those colors, it is blind to the first few 100 million years after the Big Bang. Webb is tuned precisely to that missing band. This is why JWST is not just a better Hubble. Hubble is a master of the visible and ultraviolet universe, the bright galaxies and sharp spiral arms. Webb is a specialist built to catch ancient, stretched light and to pierce the veils of cosmic dust that block shorter wavelengths. Where dust turns Hubble's view into a blank wall, Webb sees right through to the structures behind it. Tonight, we're going to treat Webb as a time machine, because that is what its orbit and instruments allow. The farther away it looks, the longer that light has been traveling, so the older the snapshot. Webb is routinely seeing galaxies as they were just 300 or 400 million years after the Big Bang, when the cosmic web should still be dim, clumpy, and unfinished. To do that, it carries a small arsenal of precision tools. NearCam, the near infrared camera, takes those deep images and measures brightness and shape, revealing which galaxies are compact, which are merging, which sit along invisible dark matter filaments. NearSpec, the near infrared spectrograph, breaks the light into spectra, letting scientists measure redshift with fine detail and read chemical fingerprints, hydrogen, helium, oxygen, even early carbon. MIRI, the mid Infrared instrument pushes to longer wavelengths, catching cooler dust and complex molecules, mapping where stars are forming inside shrouded regions Hubble could barely detect. By the end of tonight, you're going to understand why this combination is so disruptive. With these infrared eyes, the era that once looked like a blank, dark page is suddenly crowded with bright, structured galaxies. No one expects that density. No one predicts that level of maturity so soon after the Big Bang. And absolutely no one anticipates what happens when those measurements are compared to the standard model of cosmic evolution. So what exactly is this era JWST is crashing into? To answer that, the mission has to rewind the entire solar system's parent galaxy back to its childhood, and then keep going straight into the universe's first sunrise. Cosmologists call it the cosmic dawn, the moment when the first stars and the first galaxies switch on and begin to carve light out of a nearly perfect darkness. Now, let's begin. Picture a timeline stretched across your room. On the far left, time 0, the Big Bang. Space is hot, dense, blinding. Fast forward just 380,000 years, a blink on this cosmic clock, and the universe cools enough for electrons and protons to combine into neutral hydrogen. Light can finally travel freely. That fossil glow is the cosmic microwave background, the CMB, the oldest light the Planck and WMAP spacecraft have mapped. After that, everything goes dark. No planets, no stars, no galaxies. Just expanding hydrogen and dark matter. This is the Dark Age, a long, uneventful stretch running for hundreds of millions of years. Then, very slowly at first, gravity begins to win. Dark matter collapses into filaments, gas falls into those invisible wells, and the first stars ignite along that hidden scaffolding. Their ultraviolet light starts to punch holes in the hydrogen fog, ionizing it, turning neutral atoms back into a charged plasma. That slow clearing is the era of reionization. In the standard Lambda CDM picture, this transition is gentle. Tiny, dim, metal, poor galaxies form first, more like flickering campfires than cities. They sit along thin, dark matter threads, grow by mergers, and only gradually build up the kind of massive, bright systems seen in the nearby universe. By the end of tonight, you're going to understand just how confident scientists were in that story. The equations match the CMB. They match galaxy clustering. They match the large-scale Webb. But before JWST, almost everything about cosmic dawn came indirectly. The CMB shows the initial conditions, distant quasars revealed through absorption lines in their spectra when the hydrogen between galaxies goes from opaque to transparent. Hubble could glimpse some early galaxies, but only the brightest tips of the iceberg, and mostly at lower redshifts, where the universe is already more mature. JWST's entire design is a challenge to that limitation. Its infrared eyes are tuned so that light emitted in the ultraviolet and visible during cosmic dawn arrives stretched or redshifted into the infrared today. Deep fields and targeted surveys are deliberately pushed to redshifts of 10, 12, even 15. That corresponds to seeing the universe when it was just 200 to 300 million years old, less than 2% of its current age. The expectation is simple: faint smudges, sparse, primitive systems, a slow ramp, up of complexity. No one expects anything else, no one predicts a skyline. Yet when JWST stares into that epoch, the darkness is not empty. It glows with structures that look far more like bright, crowded cities than lonely campfires, setting up a direct collision between prediction and observation that the next section has to confront. The skyline shows up fast. Too fast. When JWST zooms in on that glowing epoch, it finds specific beacons that should not be there yet, galaxies with redshifts of 10, 11, 13 and beyond, meaning their light left when the universe was only 300 to 400 million years old. One famous candidate, nicknamed Glass Z13, blazed out of an early survey like a cosmic flare. Another, Sears 93316, pushed even higher. These are not shy, flickering embers. They are bright. Now, let's begin to unpack what that brightness means. Astronomers do not see the individual stars in these systems. They see blended light. From that light, spread into a spectrum, they measure how redshifted it is, which gives distance and age. Then they look at how intense the glow is across different wavelengths. Blue-leaning light hints at hot, young stars forming rapidly. Redder, smoother light suggests an older, more built-up population. By fitting models to that spectral energy distribution, scientists estimate how many stars must be packed into each galaxy and how quickly new ones are igniting. There are uncertainties. Dust can hide light. Exotic stellar populations can skew colours. Some early photometric redshifts turned out to be lower once JWST captured full spectra. Glass Z13, for instance, was revised downward after more detailed observations. But even with those corrections, the core problem does not vanish. The conservative galaxies still left standing at redshift 8, 9, 10 are not tiny. They are heavyweights. In several cases, the inferred stellar masses climb toward tens of billions of suns. One object from the Sears field, initially flagged at extreme redshift, appears to host mass on the scale of the modern Milky Way's stellar content, compressed into a time when the universe is less than 5% of its current age. Think about the schedule. Under standard Lambda CDM, matter collapses hierarchically. Small clumps merge into bigger halos, which then cool gas and form stars. It is a slow build, a cosmic construction project stretching over billions of years. Designed for that gradual timeline, Lambda CDM simulations predict that truly massive galaxies should be rare in the first few 100 million years, with the brightest systems emerging later as mergers pile up. Yet JWST's early surveys report something else, a crowded field of big, bright galaxies at high redshift. Not one oddball, an overabundance. No one expects the luminosity function to tilt that far upward. No one predicts this many skyscrapers in the supposed cosmic village. Before we get started on radical explanations, it is important to stress that the data are still being refined. Some candidates will fade with better measurements, but the trend line remains unsettling. Even the trimmed sample pushes the growth rate of structure, the efficiency of turning gas into stars, and the behavior of dark matter halos right up against, and sometimes beyond, what Lambda CDM comfortably allows. By the end of tonight, you're going to understand the stakes of that tension. Either galaxies learn to grow faster, denser, and more efficient than the standard picture allows, or the standard picture itself, the cosmological model beneath the entire mission, is the part that has to change. That tension only makes sense once you realize something unsettling. The old census of galaxies, that famous 2 trillion headline, was built on a universe where a whole layer of light was missing. Now, let's begin. Think about Hubble's deepest images, those long stares into what looked like empty space. They became icons because they turned darkness into thousands of galaxies. But they were still blind to most of the light from the very first systems. As the universe expands, it stretches light. Photons that left newborn galaxies as brilliant ultraviolet and visible glow were dragged over billions of years into the infrared. By the time they reached our solar system, much of that glow had slipped beyond Hubble's boundary. So when scientists counted galaxies in those deep fields, they were counting what the instrument could see, not everything that was actually there. The mission was tuned to optical wavelengths. The earliest, most distant systems had already had their light redshifted out of that window like a radio station drifting off the dial, while the receiver stays fixed, and that was only half the problem. Between those galaxies and the spacecraft, space is not perfectly transparent. Interstellar and intergalactic dust grains absorb and scatter visible light. They dim it, redden it, and sometimes erase it entirely. A galaxy blazing in the infrared can look faint or even invisible at optical wavelengths. The result is a bias that hides the messiest, dustiest, and often most rapidly star-forming systems. From Earth's perspective, that created a quiet selection effect. The universe looked cleaner, simpler, and less crowded than it really is because the census was dominated by the kinds of galaxies that shine through dust and sit in Hubble's favored band. The early universe that emerged from those surveys was elegant, many small, faint galaxies building up gradually over time. But that elegance rested on what the detectors could capture, not on what the cosmos actually built. JWST is the pattern interrupt. Its mirrors and instruments are tuned to the infrared, the very wavelengths that expansion and dust pushed out of Hubble's reach. Suddenly, the same patches of sky light up. Known galaxies grow brighter and more massive once their buried star-forming regions are exposed. Entirely new systems appear where there was only darkness before. It is as if someone has peeled back a veil and revealed a second image under the first. This is the hidden layer, not a separate universe, but a band of reality that was always there, shifted and shrouded just beyond our instrument's reach. Tonight, we're going to treat it like a missing frame in the film of cosmic history. And yet, even this might not be the final frame. No one predicts that JWST is the end of the story. Beneath its sensitivity, there could be an even dimmer layer still. Ultra-faint galaxies clinging to dark matter scaffolding, structures that shape the cosmic wind and gravity fields, yet remain invisible. By the end of tonight, you're going to understand why that possibility is forcing scientists to rethink what complete really means. To see what that missing layer might look like, you have to imagine the universe not as a city of glittering skyscrapers, but as a continent of ghost towns. Ultra-faint galaxies are those ghost cities of the cosmos. Tiny, fragile systems with so little light that, from across cosmic distance, they almost disappear. Now, let's begin. A normal bright galaxy might host hundreds of billions of stars. These ultra-faint systems can get by with a few million, a few 100,000, sometimes even less. Their visible stars are just a thin frosting on top of a massive invisible cake of dark matter. In terms of gravity, the dark halo is the real city. The stars are the streetlights left on at night. In the leading Lambda CDM picture, no one expects those halos to be rare. Small dark matter clumps form first, then merge and grow into larger structures. That means the early universe should be teeming with low-mass halos, like building plots waiting for construction. Some merge to build the bright, downtown's JWST is now revealing. Others remain as half-finished suburbs, never attracting enough gas to ignite into full-scale galaxies. By the end of tonight, you're going to understand why those half-finished suburbs may have done some of the universe's most important work. During the epoch of Ryanization, when the first generations of stars were turning the cosmic fog transparent, The powerhouses were not necessarily the big, showy galaxies. If ultra-faint galaxies were abundant, their countless young hot stars could have pumped out ionizing photons far beyond their weight class. 10, 100, 1,000 dim galaxies can outshine one bright one in total ionizing output. The paradox is that the more crucial they are, the harder they are to see. Their light is weak. Their stars are spread out, giving them a low surface brightness that melts into the background glow. At great distances, the expansion of space stretches their light into the infrared, where even a giant spacecraft like JWST has to fight zodiacal light, detector noise, and the glare of brighter neighbors. Some are hidden behind dust. Others are blended into the halos of larger planets of stars, lost in the glare like a candle next to a searchlight. So our grand 2 trillion galaxies census may be missing an entire dim underclass. The universe might look like a modern mega city from orbit, bright downtown cores surrounded by a vast, barely lit sprawl of neighborhoods that never make the postcards. No one predicts that count to stay fixed once the ghost cities are accounted for. Before we get started on dark matter scaffolding itself, there is one more twist. Ultra-faint galaxies may be invisible one by one, but together they still bend space. Upcoming gravitational lensing surveys and clever statistical techniques will try to read their presence from subtle distortions in background light, turning the cosmos into its own magnifying glass and revealing the hidden framework beneath the bright frontier JWST has already discovered. Those subtle distortions are the first hint. The light is bending even where almost nothing seems to glow. That's the telltale signature that there is a deeper layer in space, not made of stars, not made of gas, made of something that only reveals itself through gravity. Now, let's begin. Astronomers call it dark matter. It doesn't shine, it doesn't absorb, it doesn't reflect, but it pulls. It pulls so hard that galaxy disks spin too fast to be held together by their visible stars alone. It pulls so cleanly that galaxy clusters act like lenses, magnifying and stretching the light of even more distant galaxies into arcs and rings. And on the largest scales, it shapes where every galaxy in the observable universe is allowed to live. Picture the cosmos not as a random sprinkle of islands in the void, but as a vast three-dimensional web. In simulations of the Lambda CDM model, dark matter collapses first into filaments and dense nodes. Gas then falls along those filaments like dew beading on a spider web at dawn. Where the strands cross, gas piles up, cools, and ignites into the first stars and galaxies. The bright points are only tracing the underlying pattern of an invisible network. Tonight, we're going to treat JWST as a flashlight skimming across that web. Its infrared eyes see the luminous parts, the young stars, the glowing hydrogen, the heated dust. But compared with the dark matter, that is just the frosting. The real mass, the real architecture, is the invisible cake underneath. Every galaxy JWST discovers is embedded in a much larger dark matter halo, a gravitational cocoon that outweighs its stars by a factor of 5 or more. So when JWST finds unexpectedly massive galaxies only a few 100 million years after the Big Bang, it is not just challenging ideas about star formation. By the end of tonight, you're going to understand that it is challenging the scaffolding itself. Lambda CDM tells scientists how quickly dark matter clumps, how fast filaments grow, how early halos of a given mass should appear. The entire timeline of structure in the solar neighborhood and far beyond is tied to those properties. If the early universe looks too structured, there are only a few options. The observations are wrong, the interpretation is wrong, or the invisible skeleton is behaving in a way no one predicts. No one expects a hidden layer to rewrite the rules of gravity. Absolutely no one anticipates that faint smudges in JWST images might be the first hint that dark matter is stranger, warmer, or more interactive than the standard picture allows. And, if that's true, the next step is to go after the evidence directly, in the places where the Webb is under the most extreme tension. So if the hidden layer lives where gravity is under maximum tension, it also lives where the light does something strange. It lives in the dust. Cosmic dust sounds gentle, like the powder on a bookshelf. In space, it is a battlefield filter. It blocks, it scatters, and then, quietly, it glows. Those grains are tiny, micron scale, smaller than smoke, but they sit between you and distant galaxies like a fogged window. Starlight in visible wavelengths slams into them and never reaches the telescope. To a mission like Hubble, whole regions just look dim or empty. But that energy does not vanish. The dust heats up, then re-radiates that stolen light in the infrared, releasing a soft, diffuse glow that spreads across the sky. Tonight, we're going to lean into that glow because hidden inside it is one of the strangest accounting problems in modern cosmology. When scientists look beyond individual galaxies and ask a simple question, how bright is the universe as a whole, they are measuring something called the extragalactic background light, the EBL. Think of it as the sum of all unresolved light from every star, every galaxy, and every cloud of dust across cosmic history, smeared into a faint haze. Now, let's begin. There are two ways to estimate this background. One is bottom-up. Count galaxies, measure how bright they are, model the ones too faint to see, and add everything together. The other is top-down. Measure the total glow of the sky in infrared and optical wavelengths, then subtract all the local sources from our own solar system, our own galaxy, and our instruments. Expectation versus reality. Those two methods should match. They do not. Several measurements, especially in the near-infrared, suggest that the EBL is higher than what you get by just stacking up the light from individually detected galaxies. There is extra glow, a missing term in the equation, a light budget that refuses to balance. This is where JWST steps in as the universe's most meticulous auditor. Its mirrors and detectors are tuned exactly to the wavelengths where dust re-radiates, and its sensitivity to faint, diffuse, infrared emission lets it peel back layers that older spacecraft could only guess at. By the end of tonight, you're going to understand that when JWST stares into a region that once looked dark, it is not just seeing more galaxies. It is measuring the glow between them. No one expects that sensitivity to make the mystery go away. In some early deep fields, JWST reduces the gap by resolving more ultra-faint galaxies and more structured dust emission. But in others, questions remain. Is there still missing light, hiding in populations of galaxies so small and diffuse that even JWST only sees their combined shimmer? Or are there more exotic sources at work, decaying dark matter, primordial black holes, processes beyond the standard model? If the background is truly brighter than our catalogues allow, then the hidden layer is not optional. It is required. Either the universe is packed with a vast population of ultra-faint galaxies woven along the dark matter web, or there is a new kind of radiation source humming in the dark. And right now, the cosmic books do not quite close. JWST is still turning the pages, heading for the most extreme environments it can find to see whether light finally adds up or breaks the rules again. So if the light doesn't add up, what about the blueprint that predicted it in the first place? To understand why these galaxies are such a big deal, you have to zoom out to the master plan cosmologists use for the entire observable universe, the Lambda CDM model. Now, let's begin. In 3 symbols, Lambda CDM looks simple. Lambda is dark energy, the mysterious pressure driving the expansion of space to accelerate. CDM is cold, dark matter, invisible mass that clumps, moves slowly, and builds a cosmic web. Add a thin sprinkling of ordinary matter, the atoms that make planets, spacecraft, and you, and then set the initial conditions with quantum ripples stretched by inflation in the first fraction of a second. All of that is encoded in a handful of numbers: the matter density, the dark energy density, the Hubble expansion rate, the spectrum of those primordial ripples. This is not just a sketch, it is a working blueprint. When scientists plug those parameters into Einstein's equations and let the universe run, Lambda CDM nails the cosmic microwave background, the way galaxies cluster on hundreds of millions of light years, and the entire expansion history from the hot Big Bang to the present. No one expects one model to match so many independent observations so precisely. Yet for 2 decades, this one has. But Lambda CDM does not stop at large scales. From the same framework, supercomputer simulations grow structure from those tiny initial ripples into the first dark matter halos, then into galaxies. They predict when the first objects ignite, how many halos of a given mass should exist at a given time, and once you assume how efficiently gas turns into stars, how many bright galaxies telescopes should see in the early universe. Here is where JWST becomes a stress test. Those simulations run under Lambda CDM said the first few 100 million years after the Big Bang should be a construction zone, small, messy, and relatively dim. Instead, JWST is finding candidates that are brighter, more massive, and more common than expected at those redshifts. It is as if the cosmic city skyline appears fully built while the blueprints still show empty lots. Before we get started tearing up the blueprint, most cosmologists reach for their calculators, not their torches. The first questions are astrophysical. Are the stars in these galaxies heavier on average, pumping out more ultraviolet light per unit mass? Is dust absorbing and re-radiating light in ways the models did not anticipate? Is the initial mass function, the recipe for how many big versus small stars you get, different under these early conditions? By the end of tonight, you're going to understand why that caution matters. If small adjustments to star formation efficiency or feedback from supernova winds can reconcile JWST with Lambda CDM, the cosmic blueprint survives with new details penciled in. If not, then the tension grows. Either Lambda CDM is fundamentally sound, but missing crucial physics in how galaxies light up the dark matter web, or these galaxies are the first quiet signal that the blueprint itself, the way space, time, and matter evolve, must be revised. No one predicts rewriting the universe from a few bright smudges. But absolutely no one anticipates ignoring them either. So what happens when that blueprint is pushed as hard as it can go, and the sky still refuses to cooperate? Before we get started on tearing it down, it helps to see how carefully it was built. Cosmologists do not just wave hands and declare how many galaxies should exist. They take the early universe as measured by the cosmic microwave background, load that primordial pattern of tiny density, ripples into supercomputers, and then press play. Gravity pulls on dark matter, gas falls into those wells, stars ignite, black holes grow. In a few weeks of computing, a virtual universe evolves from a hot plasma to a web of galaxies. Tonight, we're going to stand inside those simulations for a moment. In them, space is a giant three-dimensional grid. Each cell holds dark matter and gas, obeying the equations of gravity, hydrodynamics, and expansion. Run long enough and the grid blossoms into something that looks remarkably like the real cosmic web. Filaments, clusters, voids. Before JWST, these digital universes were tuned with obsessive care to match what Hubble and ground-based telescopes saw and to respect the strict boundaries set by the microwave background. By the end of tonight, you're going to understand why that once comfortable agreement is now cracking at the edges. When those same simulations are pushed to the highest redshifts, into the era only a few 100 million years after the Big Bang, many of them go dark. They produce galaxies, but not enough. They produce bright systems, but not nearly as bright as the objects JWST is now reporting. Expectation, a slow, gentle dawn. Reality, a sky already crowded with surprisingly luminous, surprisingly massive islands of stars. So the mission shifts. Instead of asking whether Lambda CDM is dead, scientists first turn every internal knob they can find. Increase star formation efficiency, so gas in those early halos turns into stars more quickly. Soften the feedback from supernovae and black holes so those violent winds do not blow gas back out into space quite as easily. Change the assumed properties of the first stellar populations, making them more massive, hotter, more UV bright than the ones lighting today's galaxies. Some of these changes help. Turn up the efficiency and the simulated galaxies brighten. Dial down feedback and they grow earlier, in greater numbers. Adjust the stellar recipe and the same amount of mass produces more light. For a moment the plots begin to line up with JWST's counts. But there is a price. Those same settings can overshoot the number of galaxies at later times or break agreement with how heavy elements are distributed or disrupt the carefully matched history of the cosmic star formation rate. No one expects a single tweak to fix everything. The model is a tightly woven system. Pull one thread and the whole fabric shifts. Right now, the sky is sending mixed messages, early galaxies that look too mature, later galaxies that still obey the old rules. The simulations are scrambling to keep up, and the question hanging over the next section is simple. Are we just missing a hidden layer of ordinary physics, or is there something deeper lurking in the dark? So here is the uncomfortable possibility. Maybe the problem is not the physics. Maybe the problem is the question. When someone asks, how many galaxies are there? It sounds clean, like asking how many planets orbit the sun. But out in deep space, that neat category starts to fall apart. A galaxy is not a frozen object. It is a process. Systems merge, fragment, and grow. At high redshift, close to the beginning of the observable timeline, what gets called a galaxy might be a knotted stream of gas, a few bright star clusters, and a dark matter halo still pulling itself together. The boundary between a proto-galaxy and a luminous gas clump is not a sharp edge, it is a sliding scale. Change the resolution of the telescope, and the identity of the object can change with it. That is where observational definitions quietly take over. To build a catalogue, scientists have to draw lines: minimum brightness, minimum size on the sky, minimum stellar mass. If a system falls below those thresholds, the survey pipeline does not call it a galaxy. It becomes background noise or a candidate or nothing at all. The original 2 trillion galaxy estimate depended on those lines, plus models that extrapolated huge populations of ultra-faint systems Hubble could not see. Then JWST arrives and moves the goalposts. Suddenly, infrared light from dusty, distant structures that were invisible to Hubble appears on the detector. Objects that once sat below the brightness boundary jump above it. The universe has not changed. The census rules have. No one expects a simple galaxy count to survive contact with a new instrument, but absolutely no one anticipates just how radically the early universe lights up when the wavelength window shifts. And the classification problem cuts both ways. Some of the compact, blazing sources JWST detects in the first few 100 million years may not be separate galaxies at all, but multiple clumps within a single forming system, like bright knots along a tidal bridge. In other cases, what looks like one smooth blob at first glance may, under deeper exposure and sharper analysis, break into several merging galaxies caught mid-collision. Is that one galaxy, 3 galaxies, or one galaxy in 3 pieces? By the end of tonight, you're going to understand why the headline number, 2 trillion, 100 billion, or any single figure, is less important than the underlying distribution of structures across mass, brightness, and time. The universe is not a tidy list. It is a nested, evolving hierarchy: bright galaxies, dim satellites, star clusters, gas streams, and the dark scaffolding beneath them, all shaped by gravity and the solar scale physics of individual stars. Now, let's begin to treat it that way. Because once the focus shifts from counting galaxies to mapping this hidden, layered architecture, the next question becomes far sharper. What else is out there that even JWST still cannot see? So here is the twist. Even after all of that, JWST is not showing the whole system. It is only revealing the next band in a much deeper, layered structure. The constraints start with something simple and brutal: size. JWST's mirror is large by spacecraft standards, but it is still finite. That means a finite resolution, a finite collecting area, and a hard limit on how faint a galaxy can be before its light disappears into the glow of the sky. Add background noise from zodiacal light, detector imperfections, and the infrared glow of the telescope itself, and the universe does not look infinitely transparent. It looks hazy. On top of that, there is the clock. JWST has limited observing time shared across the entire mission. It cannot stare at every dark patch of space for 1,000 hours, so most regions get only a brief look. In those shallow views, thousands of ultra-faint sources blur together. They overlap in the same pixel, blending into what astronomers call confusion noise, where individual galaxies stop being distinct objects and become a diffuse fog. Push far enough in redshift or low enough in luminosity, and a galaxy effectively vanishes. Its light is stretched to wavelengths where JWST is less sensitive. Its photons dribble in too slowly, and the signal is swallowed by that fog. The boundary is not a sharp wall, but a sliding threshold. Brighter galaxies at early times stand out, while a much larger population of tiny, dim systems simply sinks below the noise floor. Every once in a while, gravity itself interrupts that pattern. A massive foreground cluster can act like a natural lens, magnifying and distorting the light from galaxies behind it. Suddenly, an ultra-faint system that would be invisible on its own is boosted into detectability. By the end of tonight, you're going to understand that each of these lensed galaxies is not just a curiosity, It is a clue that there are many more just like it, hiding below JWST's normal reach, and beneath all of that luminous structure, something even more elusive: dark matter. JWST does not see it directly. It only traces the bright tracers riding along its gravitational scaffolding, stars, gas, and dust flowing along invisible filaments. The true mass of the cosmic web, the part that never glows, remains an unseen framework. So the picture is layered. Hubble revealed the bright tip. JWST is cutting into a deeper band. But below that, there is likely a vast ocean of ultra-faint galaxies and pure dark matter architecture that no current telescope can resolve. Tonight, we're going to ask the uncomfortable question. If each generation of observatory peels back one more layer, what will the next one expose about the true depth of the cosmic web, and how far does this hierarchy of hidden structure really go? So far, the journey has taken you from a single headline number to a universe that refuses to sit still beneath it. For years, the estimate was simple: about 2 trillion galaxies in the observable cosmos. That figure came from Hubble's deepest views, plus models that filled in the invisible gaps with swarms of ultra-faint galaxies too weak to detect. The picture was crowded, but comforting. The hierarchy felt understood. Then the James Webb Space Telescope turned its mirror toward the same dark reaches of space, longer wavelengths, sharper infrared eyes, and suddenly the early universe did not look like a quiet, dim nursery. It looked busy. It looked bright. It looked old before its time. Massive, compact galaxies appeared just a few 100 million years after the Big Bang, shining far more intensely than standard models of structure formation predicted. No one expects skyscraper-scale galaxies in a cosmic era that should be building huts. No one predicts fully formed spiral-like structures when the universe's expansion and dark matter scaffolding are supposed to be in their awkward childhood. Yet that is the tension emerging from JWST's deep fields. Above the old layer of 2 trillion, there is now a new layer of confusion. Perhaps fewer ultra-faint galaxies than Hubble-era models required, but more big, bright systems far earlier than scientists thought possible. So the central questions sharpen. How many galaxies are really out there when both the visible and the invisible populations are counted honestly? Why do some of them appear so big, so bright, so early, packed with stars and heavy elements when the cosmic clock has barely started? And if the timing is off, what does that say about dark matter, about the invisible framework that guides galaxy assembly, and about the standard Lambda CDM cosmological model that underpins almost every simulation of the solar system's wider environment in the Milky Way? Tonight, we're going to turn those questions into a roadmap. From here, the mission goes narrower and deeper. First, the episode will dive into specific JWST deep fields pixel by pixel to see what the spacecraft actually recorded at the edge of the observable timeline. Then, it will slow down on a handful of impossible galaxies, case studies where mass, size, and age collide with theory at full speed. After that, the focus will shift to interpretation. Are these galaxies truly breaking the model, or are selection effects, dust, and exotic star populations playing tricks with the light? Competing teams of scientists are already proposing revisions, tweaks to star formation, new dark matter behaviors, even subtle changes to how cosmic expansion is inferred from the background glow. By the end of tonight, you're going to understand not just whether the headline number goes up or down, but how this hidden layer forces cosmologists to rethink the very architecture of the cosmic web. This is not a story of more galaxies or fewer galaxies. It is a story of a universe that adds complexity every time the boundary of observation moves outward, every time a sharper eye looks beyond the previous horizon. Before we get started on those deep fields, hold that image of a layered structure in mind. Bright galaxies on top, ultra-faint dwarfs beneath, and below even that, a dark matter skeleton and the intergalactic wind of photons and particles threading it all together. Now, let's begin. That layered image is not just poetic, it is literal. Buried under the bright, confident galaxies that Hubble made famous is a hidden majority. Ultra-faint galaxies so dim they live below the noise floor of older telescopes. These are not grand spirals or blazing quasars. They are tiny, low, mass systems with almost no stars, radiating so little light that, to Hubble, they were indistinguishable from the random grain of the detector. Their total luminosity is low, but the key problem is not just how bright they are, it is how that light is spread out. Telescopes do not only have a limit on how small and faint an object can be, they have a limit on surface brightness, on how much light arrives per unit area of sky. Spread the same number of photons over a slightly larger patch and the signal sinks into the background. At that point, the galaxy is still there. The instrument just stops being able to tell it from the glow of the sky and the electronic hiss of the detector. So when Hubble stared into its famous deep fields, it did not simply miss a few marginal dwarfs. It missed entire classes of diffuse, ultra-faint galaxies, whose light was smeared so thin that they vanished into what looked like empty space. The 2 trillion galaxy estimate tried to correct for that, using models to extrapolate how many faint systems must exist beyond Hubble's reach. But those corrections were guesses, informed by theory, not by direct detection. Tonight, we're going to let JWST push that boundary down. With a mirror more than 6 times the collecting area of Hubble, instruments cooled close to absolute zero, and vision tuned to the infrared where ancient, red-shifted starlight lives, JWST turns part of that old noise into real, countable galaxies. Patches of sky that once looked smooth now resolve into a fine spray of ultra-faint sources. By the end of tonight, you're going to understand why this matters. Ultra-faint galaxies are not just numerical padding that make the universe's census look impressive. They trace the smallest clumps of dark matter, the first places where gas cooled and formed stars, the fossil imprint of how structure assembled from the bottom up. Change their abundance or their properties, and the entire cosmic growth history shifts. No one expects the hidden majority to be the same everywhere. Yet JWST is hinting that these ultra-faint galaxies form a kind of cosmic background texture, a woven layer of structure underlying the bright, easily counted systems, and in some regions they seem richer and more organized than models predicted. If that hidden layer is different from what those models assumed, then the extrapolated 2 trillion is not just off by a rounding error. It may be systematically biased. And the real surprise is not only how many of these faint galaxies there are, but how early they appear and how mature some of them already look, as if the universe learned to build quickly, and on a plan we have not yet fully uncovered. If that hidden layer is different, the next question is brutal. How do you see galaxies that are, by definition, too faint to see? Even with JWST staring for tens of hours, countless systems stay buried below the noise. They're there. Their light reaches the mirror, but in a single exposure they vanish into the random grain of the detector. This is where astronomers start doing something that feels almost like cheating. They stop looking at one image and start looking at hundreds. Now, let's begin. Imagine taking a dark, noisy photo of a candle across a foggy field. One frame shows nothing but static. But if you take that same photo again and again, always pointed at the same spot, and then average all the frames, something happens. The random noise cancels down. The steady, real signal adds up. Suddenly a faint glow appears where there was only darkness. That is image stacking. The signal from a galaxy is coherent. The noise is not. Combine 10 images, the signal grows by 10, while the noise grows more slowly. Combine 100, and features invisible in each single frame rise above the noise floor. JWST's deepest fields are not one heroic exposure. They are towers of images, stacked and aligned, until the universe gives up its weakest whispers. But scientists do not stop at stacking images, they stack galaxies. By the end of tonight, you're going to understand how strange that sounds and how powerful it is. Take thousands of ultra-faint candidates that are each barely or not at all detectable. Align them on their centers, average them together. Individually, they are ghosts. Together, they form a sharp, average profile of a galaxy that no single spacecraft frame could reveal. It gets wilder. Space itself helps. Massive galaxy clusters act as natural telescopes. Their gravity bends and magnifies light from even more distant systems behind them, a phenomenon called gravitational lensing. The cluster distorts the background like a cosmic funhouse mirror, stretching tiny galaxies into long, thin arcs and boosting their brightness by factors of 10 or more. In a JWST deep field behind a massive cluster, the scene looks chaotic at first glance. Dozens of faint, curved streaks wrapped around the central mass. Those arcs are galaxies that would otherwise sit far below JWST's detection boundary, pulled into view by gravity alone. No one predicts the universe will hand over free magnification like this, and absolutely no one anticipates how crowded the lensed background turns out to be. These tricks do more than pad the galaxy census. By counting how many faint systems appear at each brightness, with and without lensing, scientists pin down the luminosity function at early times, the full distribution of galaxy brightnesses, instead of just the obvious showpieces. So the hidden layer stops being a guess. It becomes a reconstructed population inferred from statistical shadows and gravitational distortions. And when that richer, faint-end population is plugged into models of the early universe, the timeline of reionization and the growth of structure does not just shift slightly. It starts to twist in ways that challenge the standard story. So, if the faint-end population twists the story, reionization is where the plot really breaks. The early universe does not just grow structures, at some point it turns the lights on. After the Big Bang cools and the first atoms form, space enters the cosmic dark ages. Hydrogen is neutral, fogging the cosmos in ultraviolet shadow. Then, hundreds of millions of years later, the first stars and galaxies ignite. Their high-energy photons slam into that neutral hydrogen, strip off electrons, and reionize the intergalactic medium, turning the universe transparent to ultraviolet light. In the standard picture, this is a slow burn, not a flashbulb. Tiny, faint galaxies form first, in small, dark matter halos. They are fragile, inefficient, and dim. Over hundreds of millions of years, more halos collapse, more stars form, more photons leak out. By around 1 billion years after the Big Bang, the universe is supposed to be mostly reionized, a gradual dawn rather than an instant sunrise. Now, let's begin to compare that textbook dawn with what JWST is actually seeing. Point this spacecraft at regions that, in Hubble's deepest images, looked nearly empty, and the infrared view explodes with galaxies, not just wisps. Surprisingly bright, surprisingly massive systems already in place 300 to 500 million years after the Big Bang, and layered beneath them hints of an enormous population of ultra-faint galaxies right at the edge of detectability. Reionization becomes a cosmic whodunit. Who supplied the missing photons that cleared the fog so quickly? To answer that, scientists do something deceptively simple. Count galaxies, measure how bright they are, then fold in assumptions about how many ionizing photons each stellar population produces and how many of those photons actually escape their galaxies instead of being trapped by gas and dust. When those ingredients are combined with JWST's early counts, something snaps. Even conservative analyses suggest that early galaxies may have produced more ionizing radiation earlier than Lambda CDM-based models predicted. The boundary between dark ages and cosmic daylight seems to move forward in time, as if someone turned up the dimmer switch long before the script allowed. That leaves a stark choice. Either star formation ramped up much faster than expected, or those first stars were far more efficient ionizers, perhaps metal-poor, massive population 3, like stars that blast out ultraviolet light, or there are additional hidden sources, faint, active galactic nuclei, buried black holes, compact, dust-cloaked engines that Hubble could not see. Tonight, we're going to follow that trail into the hidden layer, because the missing reionization budget may live in galaxies too faint, too obscured, or too tightly packed for previous telescopes to resolve, but now starting to surface in JWST's data. If the universe lit up faster than expected, then something about how matter clumped, cooled, and collapsed into structure is wrong in the standard mission briefing. And absolutely no one anticipates what that implies for the rest of cosmic history. Those first hints of a universe that lit up too quickly lead straight into one of JWST's most unsettling discoveries. Staring back to redshifts around 10, 12, even 13, scientists are finding what look like full-grown cities in a cosmos that should still be laying foundations. Galaxies whose stellar masses rival or even exceed the Milky Ways when the universe is only a few 100 million years old. In the standard Lambda CDM mission briefing, structure in space grows slowly and hierarchically. Tiny dark matter halos form first, then merge into larger halos, which gradually pull in gas, cool it, and build up stars over hundreds of millions, then billions of years. You start with cosmic villages, then towns, then cities. No one expects skyscraper-scale galaxies to be standing in the first construction season, yet that is what these overachiever galaxies seem to be. Too big, too soon. Their light reaches JWST as faint smudges in the infrared, stretched by cosmic expansion, but when scientists decode that light, the numbers escalate fast. By the end of tonight, you're going to understand why those numbers are giving theorists a headache. Mass in astronomy is almost never weighed directly. It's inferred. JWST measures how bright these galaxies are across many wavelengths, building a spectral energy distribution. Then models are fitted that say if you have this color, this brightness, and a reasonable history of star formation, here is how many stars you must contain. Different stellar populations, different ages, different amounts of dust all tweak the answer, but they do not erase the central surprise. Some of the earliest claims were extreme. Candidates at redshift 13 with stellar masses apparently similar to the present-day Milky Way. That triggered a wave of re-analysis. Spectra were checked, redshifts refined, assumptions about star ages and metallicity dialed back. As expected, some masses shrank. A few record breakers quietly stepped down from the podium, but the population did not vanish. Even with conservative models, there remains a substantial group of galaxies that simulations say should be rare outliers, not common residents. The boundary between prediction and observation is not a thin line. It is a widening gap. Now, let's begin to ask why. Either their dark matter halos collapsed earlier and faster than Lambda CDM typically allows, or gas inside those halos cooled and formed stars with astonishing efficiency, converting a large fraction of available baryons into light in record time. Or the early stellar populations themselves are different, skewed toward massive, brilliant stars that make galaxies look heavier than they are. And beneath these overachievers, there is almost certainly a hidden layer. For every galaxy JWST can see, there could be many more that are smaller, dimmer, dustier, sitting along the same dark matter scaffolding but still below the detection threshold. The universe, even this early, begins to look less like a smooth, gentle fog and more like a crowded, rapidly wiring cosmic web. Some cosmologists are tempted by more exotic fixes, dark matter with unusual interactions or a brief phase of early dark energy that accelerates structure growth. No one predicts consensus on those ideas yet. The community is carefully testing the conservative options first. But if galaxies really grew this fast, this early, what does that say about the invisible framework that guided them? If the galaxies are too big, too soon, is the dark matter web itself behaving differently than expected? To answer that, you have to peel back another layer of the universe. Beneath every galaxy JWST sees, beneath the whole 2 trillion galaxy picture, there is a hidden framework, the dark matter cosmic web. Now let's begin. In the standard Lambda CDM model, space is not just a random sprinkle of galaxies. It is a vast network of invisible filaments and dense nodes, a 3-dimensional spider web made of dark matter. Gas flows along those filaments like rivers following valleys, piling up at the intersections. Those intersections become dark matter halos, and inside those halos, the first stars and galaxies ignite. The strange part is that no one has ever seen this web directly. Dark matter does not shine, does not absorb light, does not act like any familiar material in the solar system. Scientists infer it from its gravity. Galaxy disks rotate too fast in their outer regions. Without extra, unseen mass, they should fly apart. Gravitational lensing bends light from background galaxies more strongly than visible matter alone can explain. On the largest scales, the statistical pattern of galaxy clustering matches a universe dominated by an invisible component. Before we get started on JWST's role, picture how this web is predicted to form. Simulations begin with tiny quantum fluctuations in the infant universe, imprinted in the cosmic microwave background. Then they let gravity, expansion, and dark matter run. Over billions of years in the computer, those tiny ripples grow, merge, and stretch into a web, like pattern of filaments, sheets, and nodes. The result lines up with many large-scale observations, galaxy superclusters, cosmic voids, and the average properties of the intergalactic medium. But JWST is not looking at the web itself. It is looking at the lanterns hanging on it. The timing, abundance, and clustering of early galaxies trace, when and where dark matter halos collapsed along that web. If galaxies appear too early, too massive, or too tightly packed, the underlying dark matter peaks must have grown faster or differently than Lambda CDM expected. That is exactly where the tension begins. In some JWST deep fields, astronomers see hints of clusters, over-densities of galaxies already assembling just a few 100 million years after the Big Bang. Several bright galaxies crowd the same tiny patch of sky at nearly the same redshift, like a skyscraper district rising long before the surrounding town exists. By the end of tonight, you're going to understand why that matters. If the early galaxy web looks too developed compared to simulations, Lambda CDM is being stress-tested. Maybe dark matter clumps more efficiently. Maybe baryons respond to halos in ways the models missed. No one expects a single JWST image to overthrow the standard model, but absolutely no one anticipates how hard these early structures are pushing it. Beneath every bright JWST galaxy lies an invisible dark matter halo. Beneath the familiar map of galaxies lies a deeper, darker architecture, a cosmic web we cannot see directly, but which shapes everything we can. And JWST is starting to sketch its first faint outlines. Dark matter is the invisible skeleton. But there is another veil much closer to the light itself, a veil made of smoke. In space, that smoke has a name: cosmic dust. Not dust like under a bed, but tiny, solid grains, often smaller than a micron across, drifting through the solar system, between the planets, and through the vast gulfs between galaxies. Scientists think these grains are forged in the violent winds of dying stars and in supernova explosions, then mixed into the cold gas clouds that will build the next generation of suns and worlds. Now, let's begin with what that does to light. Dust is incredibly efficient at absorbing and scattering ultraviolet and visible wavelengths. Shine starlight through a dusty cloud, and the blue light vanishes first, the way distant mountains look redder and dimmer through Earth's atmosphere. On galactic scales, the effect is extreme. Whole star-forming regions and sometimes entire galaxies can be dimmed into obscurity or rendered effectively invisible to optical telescopes. So, where does that missing energy go? It does not disappear. The grains heat up just a little and re-emit the stolen starlight in the infrared. A galaxy that looks like a faint smudge or nothing at all in Hubble's sharpest images can blaze like a beacon when seen at longer wavelengths. To Hubble, those systems hug the boundary of detection. To JWST, they light up the sky. Tonight, we're going to follow those hidden embers. Astronomers call the most extreme examples dusty star-forming galaxies, or DSFGs, and submillimeter galaxies. These are cosmic factories where stars are being born at hundreds, sometimes thousands of solar masses per year, buried behind curtains of dust. In optical surveys, they might look like a few lonely pixels. In the infrared and submillimeter, they are among the brightest galaxies in the universe. Before we get started with the early universe, remember the expectation. Young galaxies close to the Big Bang should be relatively clean. Not many stars have lived and died yet, so not much dust. JWST is already breaking that picture. Its first deep fields revealed surprisingly dusty galaxies at high redshift, only a few 100 million years after the beginning. No one expects that level of chemical maturity so soon. To have that much carbon, silicate, and metal locked into grains, several generations of massive stars must already have formed, exploded, and enriched their surroundings. That changes the census. The original 2 trillion galaxy estimate leaned heavily on galaxies Hubble could see, then extrapolated to fainter, smaller systems. But dust-obscured galaxies were undercounted, especially in the early universe. The result was a biased map, tilted toward cleaner, less dusty systems that cooperate with optical telescopes. By the end of tonight, you're going to understand that some of the missing galaxies and a large fraction of the missing star formation are literally hiding behind their own smoke. JWST's infrared cameras and spectrographs cut through that haze, turning apparent voids into crowded neighborhoods. Picture one deep field. In Hubble's view, a sparse sprinkling of distant points. In JWST's infrared, the same patch becomes a glowing metropolis. Warped, reddened, dust-enshrouded galaxies crowding every corner of the frame, revealing that even the dark sky between the known structures hides yet another layer beneath. Those glowing metropolises of early galaxies don't just look dramatic. They walk straight into the heart of our best cosmic theory and start asking hard questions. Now, let's begin with the framework that everything is being tested against. Lambda CDM, lambda, cold dark matter. It is the standard model of cosmology, the blueprint that says the universe is dominated by cold dark matter, plus a cosmological constant, dark energy, driving the accelerated expansion of space. With just a handful of parameters, it traces the evolution of the entire observable system, from the Big Bang to the present. By the end of tonight, you're going to understand why scientists are nervous, but not panicked, because Lambda CDM has earned its authority. It nails the tiny temperature ripples in the cosmic microwave background, matching their spectrum and amplitude with exquisite precision. It reproduces baryon acoustic oscillations, those frozen sound waves in the early plasma that set a preferred scale in galaxy clustering. It gets the large-scale web of galaxies right, and it delivers a universe with the correct age, geometry, and expansion history. On the biggest scales, it works. Then, JWST looks into that hidden layer beneath the cosmic wallpaper, and the tension begins. No one expects to see so many bright, massive galaxies when the universe is only a few 100 million years old. Yet, JWST has discovered candidates that seem too big, too soon, shining with more starlight than standard formation timelines prefer. It finds dust and heavy elements, metals appearing earlier than models predicted, and hints that the faint galaxy population might be richer or differently distributed than the extrapolations behind that famous 2 trillion galaxies estimate. Here's the key distinction. These are not yet fatal blows to Lambda CDM on cosmic scales. They are challenges to how structures assemble inside that framework, especially at early times and on relatively small scales. The dark matter scaffolding and the overall expansion can stay intact, while the recipes for turning gas into stars, for driving winds, for building galaxies come under review. So theorists go back to the numerical laboratories, they crank up star formation efficiencies, they tweak feedback from supernovae and black holes, they experiment with more top-heavy initial mass functions and faster dust production in the first generations of stars. The question is simple. Can more extreme but still plausible physics inside Lambda CDM reproduce what this new spacecraft is seeing beyond the reach of Hubble? Some of those fixes work only if parameters are pushed to the edge of credibility. No one predicts galaxies that form nearly every possible star they can, with feedback turned down to a whisper. But that is the kind of regime some simulations are now exploring. At what point are we just stretching Lambda CDM to fit? And at what point are real cracks opening that demand new ingredients? Before we get started on declaring a revolution, caution matters. Early JWST data are still being calibrated. Selection effects, photometric redshift errors, lensing magnification, and model assumptions about galaxy light can all bias first impressions. Lambda CDM is not dead, but it is under the sharpest scrutiny it has faced in decades, and you are watching the trial in real time. The verdict will depend on what JWST uncovers next in that hidden layer of the universe. So when the verdict is uncertain, where do scientists go? They walk into a control room that doesn't look at the sky at all. It looks at code. Tonight, we're going to step into that room where entire universes are born inside supercomputers and aged in fast forward to confront what JWST has just discovered. These are cosmological simulations like Illustri's Eagle and Fire. Think of them as digital universes where dark matter and gas are poured into a giant three-dimensional box and allowed to evolve under gravity, hydrodynamics, and radiation. No planets, no spacecraft, just raw ingredients and the laws of physics run over billions of years of simulated cosmic time. Before we get started, there's a crucial detail. These simulations do not make up their own starting point. They begin with initial conditions calibrated to the cosmic microwave background, that baby picture of the universe taken 380,000 years after the Big Bang. Tiny ripples in that radiation map are translated into slightly denser and slightly emptier regions of dark matter and gas. Then the code presses play. As the virtual universe expands, dark matter collapses into halos. Gas falls into those halos, cools, and forms stars. Galaxies assemble along a cosmic web, exactly as Lambda CDM predicts. By the end of tonight, you're going to understand why that process is now being tested, like never before. No one expects these original simulation campaigns to perfectly match what JWST is seeing at 200 or 300 million years after the Big Bang. So a new wave of missions in silico is launching. Higher resolution, earlier start times, more extreme recipes for how stars ignite and how supernova winds blow gas back out. The goal is simple. Can tweaking the hidden rules make too big, too soon galaxies appear as often as JWST claims they do? For example, scientists can turn up the star formation efficiency in small halos, letting a larger fraction of their gas become stars very quickly. Or they can assume a more top-heavy initial mass function where massive, short-lived stars are more common. In these runs, bright, compact galaxies emerge earlier, pushing the simulated universe closer to JWST's glare. But the code tracks more than starlight. It follows metals forged in stellar cores, dust grains that soak up ultraviolet radiation, and the radiation fields themselves. That means the spectra of simulated galaxies, their chemical fingerprints and dust content, can be compared directly to JWST's measurements, line by line. Here is the tension. Some modified simulations do produce earlier, brighter galaxies, yet they often overshoot later in cosmic time, creating too many stars, too many metals, or a rayonized universe that conflicts with other observations. Fix the early boundary, and the later universe breaks. Hidden in these runs is a pattern. The models that come closest to matching JWST usually lean on a swarm of small, faint galaxies and diffuse structures, barely detectable even now, to drive reionization and chemical evolution. The visible giants ride on a deeper, dimmer layer. No one predicts the simulations will get everything right on the first try, and absolutely no one anticipates they will be the final word. The real progress lives in the back. And fourth, JWST reveals a mismatch. The digital universes are rebuilt, and every failure points to what is still missing in that hidden layer we are just beginning to see. Now, let's begin to ask what those missing pieces might actually be. By treating the universe the way an archaeologist treats an ancient city, not as a single ruin, as a layered record. Every galaxy JWST sees at high redshift is not just a dot of light on a black screen, it is a time capsule, a fossil whose bones are written in its spectrum. Before we get started on the details, picture what JWST really captures. The spacecraft is not just taking pretty images in space, it is spreading that faint, ancient glow into rainbows of infrared light, measuring how bright each tiny slice of wavelength is. Hidden in those rainbows are sharp notches and spikes, the spectral lines that tell scientists what elements are present, how fast they are moving, and how violently stars are being born. Here is where cosmic expansion enters the story. As the universe grows, it stretches the very fabric that light travels through. Wavelengths get pulled to the red, a phenomenon called redshift. Light that left a young galaxy in the ultraviolet or visible bands arrives billions of years later in the infrared. Diagnostic fingerprints that once lived in the optical, like hydrogen's Balmer lines or oxygen's O3 emission, are dragged into JWST's sweet spot. The telescope is tuned to the ancient language of a younger cosmos. By the end of tonight, you're going to understand why those lines are so powerful. Strong hydrogen emission marks raw, massive stars igniting in dense gas clouds. Oxygen and carbon lines trace how many generations of stars have already lived and died, seeding the interstellar medium with heavier elements. The overall continuum shape, rising or falling across wavelengths, reveals how much dust is present and whether it is hiding whole populations of young stars from view. Consider one concrete example. JWST targets a galaxy less than 600 million years after the Big Bang. In the raw image, it is a smudge. In the spectrum, it explodes with information. Towering O3 and hydrogen lines, ratios that scream intense, recent star formation, and metallicities surprisingly high for such a young system. Expectation. A primitive object, barely enriched. Reality. A chemically busy environment where stars have already lived fast and died, enriching the gas with oxygen in record cosmic time. Now, scale that up. Collect spectra for galaxies at many different redshifts, from 300 million to several billion years after the beginning, and a timeline appears. Star formation rates rise and fall, metal content climbs, dust thickens. Layer by layer, JWST is reading the fossil record of how quickly stars, metals, and dust filled the cosmic web. Here the hidden layer becomes crucial. Ultra-faint and dust-obscured galaxies, nearly invisible to optical missions, show up in the infrared with outsized spectral signatures. They look small in the images, but they punch far above their weight in the fossil record, revealing brief, furious episodes of star formation that Hubble never saw. Some spectra even show very hard radiation fields and bizarre line ratios. No one predicts these combinations in ordinary galaxies. They may signal exotic stellar populations or nascent black holes already carving out cavities in the early interstellar wind. This is spectral archaeology. This is how scientists test whether that hidden layer is just a dimmer version of the galaxies in the local solar neighborhood, or a fundamentally different population that forces the entire system of cosmology to be rewritten. Those strange spectra are just the beginning, because buried inside some of those tiny, red-shifted smudges, scientists are seeing something far more violent, black holes that look fully grown while the rest of the universe is still learning to walk. Before we get started on JWST, remember this. Even with older telescopes, astronomers had already discovered quasars less than 1 billion years after the Big Bang, powered by black holes weighing billions of suns. Designed as a gradual story of structure growth, the standard cosmological model suddenly had skyscrapers rising in a cosmic village that was supposed to be mostly empty. Now, let's begin with what JWST adds. Tonight, we're going to push that problem earlier, much earlier. JWST is spotting galaxies at redshifts of 8, 10, even beyond, where the light left when the universe was only a few 100 million years old. Inside some of these systems, there are candidates for actively accreting black holes, AGN, lighting up their galactic centers like miniature quasars at the dawn of time. How can scientists tell? The trick is in the fingerprints. In spectra, they see broad emission lines smeared out by gas whipping around a massive object at thousands of kilometers per second. They see high ionization features, elements stripped of multiple electrons demanding an intense radiation field. They see excess infrared and in some cases X-ray emission that no combination of young stars can explain. Something compact, hot, and hungry is feeding. Here is the growth problem. Start with a black hole left over from a massive star, maybe tens of solar masses. Let it accrete at the Eddington limit, the standard rate where radiation pressure balances gravity. There is barely enough time to climb to hundreds of millions, let alone billions, of solar masses before JWST sees it. Expectation, leisurely growth over cosmic ages, reality, monsters that grew overnight. No one predicts that outcome without new physics or new environments. So, several solutions are on the table. One idea is direct, collapse black holes, giant gas clouds in the early universe that skip star formation and collapse straight into seeds of 100,000 suns or more. Another invokes super Eddington accretion, short, furious episodes where matter pours in faster than radiation can push it back. A third leans on dense, turbulent regions where mergers and inflows funnel gas efficiently into galactic centers. All of these feed back into the hidden layer. If early black holes are more common or more massive than expected, their radiation can help ionize hydrogen. Their jets can heat the intergalactic medium, and their gravity can sculpt how nearby galaxies assemble along the dark matter scaffolding. Some JWST candidates are still under debate. Extreme starbursts can mimic AGN signatures, and at these distances, every photon is precious. But the trend is clear. An early universe richer in black holes, richer in energy injection, richer in complexity than absolutely no one anticipates from a quiet, gradual dawn. By the end of tonight, you're going to understand why this matters. Did the universe's first monsters help carve the hidden layer of structure we see today, or are they merely a symptom of deeper physics waiting just beyond our current boundary of understanding? Those monsters are the first hint that the universe is not a single smooth picture. It's a stack, a universe of layers. What you see in bright galaxies is only the top sheet of a much deeper cosmic blueprint hidden underneath the glare. Now, let's begin to peel that structure apart. The most obvious layer is the luminous one, the big, bright galaxies and quasars that dominate classic Hubble images, the ones that carried scientists to that famous estimate of roughly 2 trillion galaxies. That count came from what could be seen, then extended with models that tried to guess how many smaller systems were hiding just below the detection limit. Beneath that lies the faint structural layer, dwarf galaxies, ultra-faint smudges, star systems whose entire mass rivals a single bright region in the Milky Way. These are the bricks that build the larger cities of space, and they were mostly inferred rather than directly discovered. Before JWST, no one predicts just how crowded that layer might be in the first few 100 million years. Then there is the obscured layer, galaxies buried in their own dust, where young stars burn hot, but their light is trapped, scattered, and re-emitted in the infrared. In optical light, those systems are nearly invisible. In infrared, they flare into view as dusty starbursts, pouring energy into the cosmic web while pretending to be empty darkness. Deeper still is the invisible layer, dark matter halos forming the scaffolding, dark energy driving the expansion of the whole system. Diffuse radiation backgrounds from the cosmic microwave background to the infrared and radio glow that fills the space between planets and galaxies. This layer cannot be seen directly, but its gravity, its pressure, and its fossil light define the boundary conditions for everything else. Tonight, we're going to treat each telescope as a kind of X-ray for one of these layers. Optical observatories catch the luminous sheet. Radio arrays trace cold gas and synchrotron halos. CMB experiments map the oldest radiation surface, and infrared missions bridge the gaps, revealing what was missing between those views. JWST is that bridge made real. Its infrared eyes reach beyond the bright layer down into the faint dwarfs and the dust-choked star factories at redshifts, where the universe is only a few 100 million years old. The old 2 trillion galaxy estimate leaned heavily on extrapolations from the luminous layer. Now, JWST is directly sampling the deeper structure those models could only sketch. The challenge is to reconcile all of this into one coherent story. Dark matter scaffolding, baryonic physics, radiation backgrounds, and the strange early giants must all fit on the same layered canvas. The most serious tensions, like galaxies that seem too big too soon, or dust appearing earlier than expected, live right at the interfaces between layers, where very different kinds of physics collide. By the end of tonight, you're going to understand why those collisions may force a rethink of more than galaxy counts. Up next, the layered view starts to bend our assumptions about time, distance, and what the phrase observable universe really means. So when a telescope like JWST seems to bend our assumptions about time and distance, it is really pushing against a deeper boundary. What light can reach us at all? To understand the hidden layer beneath 2 trillion galaxies, the geometry of space and time has to come first. Now, let's begin with redshift. Cosmological redshift is not just light losing energy as it travels. It is the stretching of light, because the space between galaxies is expanding. As that space stretches, every wave of light traveling through it stretches too, sliding from blue to red, from visible to infrared, from something our eyes could see to something only a cryogenic space observatory can detect. The farther a galaxy is, the more space has expanded while its light was in flight. That means higher redshift also means greater look-back time. You are not just seeing a distant object, you are seeing that object when the universe itself was younger, when the whole cosmic system was denser and hotter. Here is the catch. The universe is 13.8 billion years old, but the observable universe is not 13.8 billion light-years in radius. It is about 46 billion. The reason is that while the light was traveling toward us, space kept expanding, carrying those galaxies farther away even as their photons raced in. Distance grew under the light's feet. To keep this straight, cosmologists use 2 ideas. Look-back time is how long the light has been traveling. Co-moving distance is how far away that galaxy would be right now if the expansion could be frozen for a moment. Think of a pattern painted on a balloon. The time it takes for light to cross the balloon is one story. The way the pattern separates as the balloon inflates is another. All of this lives inside a light cone. Picture a cone stretching upward from the Big Bang to today. Every event inside that cone can, in principle, send light to this solar system. JWST, by reaching to higher and higher redshift, is climbing closer to the tip of that cone, toward the first few 100 million years after the beginning, but that cone is not the whole universe. The famous estimate of roughly 2 trillion galaxies refers only to the galaxies inside our observable bubble, inside our particle horizon. No one predicts that the universe simply ends there. It may extend far beyond what any spacecraft or telescope can probe. It may be effectively infinite. Even within our horizon, there is a hidden layer. Galaxies so faint their light is drowned in foreground glow. Galaxies so redshifted their photons are stretched beyond previous detectors. Structures buried behind curtains of dust. JWST is shrinking that invisible zone, revealing systems that earlier missions never knew existed. And cosmic expansion writes an even harsher rule. Because the expansion is accelerating, there are event horizons, regions whose light emitted now will never reach us, no matter how long the mission of civilization lasts. By the end of tonight, you're going to understand that some layers are not just unseen, they are unseeable, locked forever beyond our light cone, baked into space-time itself. If some regions are unseeable in principle, how do scientists dare to say there are 2 trillion galaxies in the observable universe? That number sounds absolute. It is not. It is a model built from tiny keyholes on the sky and a chain of assumptions reaching far beyond what any telescope has directly seen. Now, let's begin. You cannot scan the entire celestial sphere galaxy by galaxy. The mission would outlive the solar system. Instead, astronomers take exquisitely deep images of small, carefully chosen patches, then scale up. A few square arc minutes from a Hubble ultra-deep field become a statistical stand, in for the whole sky. From that stand in, they extrapolate not just across area, but across brightness, including galaxies too faint to register at all. To do that, there is a crucial tool, the galaxy luminosity function. Think of it as a census curve for space, telling you how many galaxies exist at each luminosity. At the bright end, where massive galaxies live, the numbers drop off sharply. At the faint end, the curve rises as dwarf galaxies multiply. A Schechter function stitches these behaviors together, an exponential cutoff for the brightest systems and a power law slope for the dim swarms below. Hubble pinned down the bright and moderately faint parts of this curve across cosmic time. It could see Milky Way, scale galaxies and many dwarfs, especially at low redshift. But below its detection limit, the function had to be extended using theory and simulations. Before we get started on JWST's revolution, remember this. The faint end slope was guessed, not measured in the earliest, most distant epochs. The famous 2 trillion number came from integrating that Schechter curve over all luminosities within the observable volume. Change the faint end slope by a small amount, and the integral changes a lot, because ultra-faint galaxies dominate the raw counts. The result is a universe numerically ruled by objects Hubble never directly saw. Tonight, we're going to watch what happens when a new spacecraft starts dragging those ghosts into the light. JWST pushes deep into the infrared where early and dust-shrouded galaxies glow. It is now detecting galaxies several times fainter and at higher redshift than Hubble could manage. That means the faint end slope is no longer a free dial. It is something that can be constrained, especially in the first few 100 million years after the Big Bang. No one expects this recalibration to be gentle. If JWST finds that the faint end slope is steeper than assumed, then the hidden layer is even richer. More dwarfs, more small halos, perhaps more than 2 trillion galaxies. If the slope flattens or even turns over, the total count could drop, telling us that structure formation was less bottom-heavy than the models predicted. Complicating everything are galaxies that hide in plain sight, dust, obscured starbursts glowing fiercely in the infrared, and ultra-compact systems that blur into stellar points both bias raw counts. Wavelength surveys, lensing corrections, and careful modelling of selection effects are now being folded back into the luminosity function. By the end of tonight, you're going to understand that the number of galaxies is not a fixed headline, but a moving target, sharpened with every new JWST deep field, and in the next section, that moving target is going to collide with our deepest theories of how the cosmic web assembled. That moving target is important, but here's the twist. The universe is not a scoreboard. Whether the final tally lands at 1 trillion, 2 trillion, or 5 trillion galaxies is not the headline that really matters. What matters is the pattern behind those numbers. Think of it this way. A satellite image of Earth that only told you how many cities exist would be almost useless. The power comes from where those cities are, how big they are, how they connect. In space, galaxies play the same role. Their distribution, their masses, their environments encode the deep rules of the cosmic game. Rules written by dark matter, dark energy, and the physics of gas cooling and star formation. Astronomers don't just count galaxies, they count them as a function of redshift, mass, and neighborhood. How many dwarfs versus giants at redshift 8? How many lonely galaxies in the cosmic voids versus dense clusters where hundreds crowd together? Those curves and histograms are not just bookkeeping. They are direct tests of how quickly the invisible dark matter scaffolding collapsed, how efficiently gas fell into those wells, and how fast early stars lit up and blew that gas back out. This is where clustering statistics come in. Tonight, we're going to step beyond the simple idea of more or fewer galaxies and into the question of how strongly they clump on different scales. On tens of millions of light years, the cosmic web should grow in a very specific way in the standard Lambda CDM model. Change the behavior of dark energy, or tweak gravity itself, and the pattern of clumps and filaments changes. No one predicts those patterns by eye. They come from supercomputer simulations, and the sky either agrees or it doesn't. Inside the galaxies, the story gets even sharper. The relative abundance of quiescent versus star-forming systems, dusty starbursts versus clean blue disks, dwarfs versus giants, tells scientists how violent feedback from supernovae and growing black holes really is. Too many dead, quenched galaxies too early, and the feedback is too strong. Too many hyperactive starbursts, and it is too weak. Now, let's begin to see why JWST is such a turning point. Its infrared eyes let this spacecraft dissect internal properties of galaxies when the universe was only a few 100 million years old. Not just how many galaxies existed then, but what kinds dominated each epoch. Compact, red nuggets, chaotic clumps, buried active nuclei. In that hidden layer, ultra-faint dwarfs, dust-choked starbursts, and early AGN lurks the key to reionization, to the first heavy elements, to the moment the familiar Hubble sequence of spirals and ellipticals emerged. JWST is asking whether the early cosmos was just a scaled-down version of today's universe, or a qualitatively different regime with its own rules. And in the final act, that question is going to circle back to us, what it means for a species on one planet in one galaxy to discover that the foundations of cosmic history are stranger and more layered than anyone expected. So where does that leave the map that everyone thought was finished? For years, the universe looked like a solved puzzle. A smooth early glow, a gentle rise of structure, and, stitched on top, a confident estimate of about 2 trillion galaxies in the observable cosmos. Tonight, we're going to redraw that picture. The old expectation is clear. In Lambda CDM, the first few 100 million years are supposed to be quiet. Tiny ripples in the primordial plasma grow slowly, dark matter gathers into halos, and only later do bright, well-organized galaxies and active black holes turn on. Reality, as JWST is showing, is louder, faster, and more crowded. When this spacecraft stares back to 300 or 400 million years after the Big Bang, it does not see a timid dawn. It sees entire cityscapes of light, more galaxies than expected, earlier than expected. Some are ultra-faint dwarfs, hugging the dark matter scaffolding. Some are buried in dust, where newborn stars and metals glow in infrared wavelengths that only JWST can detect. Some are massive overachievers, with stellar masses and star formation rates that look more like young modern galaxies than fragile cosmic infants. On top of that, there are signs of active black holes already feeding in the first few 100 million years, injecting energy and wind into their surroundings. No one predicts that combination of abundance, mass, dust, metals and black hole activity so early, at least not in that concentration. Put together, these discoveries tell a single story. The universe structured itself faster and with more complexity than the clean Lambda CDM sketches implied. By the end of tonight, you're going to understand that this is not cosmology collapsing. It is cosmology being stress-tested at its weakest boundary. Lambda CDM still nails the large-scale expansion, the cosmic microwave background, the overall web of dark matter and galaxies. JWST has simply zoomed into the regime where those broad-brush models were least constrained and has started to expose the fine print that was missing. Think of it as swapping a textbook diagram for a terrain map. The old version showed a smooth, slowly brightening universe. The new version is clumpy, dynamic and layered. Bright giants, faint dwarfs, dusty starbursts and dark scaffolding all share the same early space, woven into a system that Hubble could not fully see. Beneath the familiar constellation of big, obvious galaxies, a hidden layer has been discovered. An underworld of barely there smudges and buried engines that now has to be counted. For decades, that 2 trillion galaxy number felt like bedrock, a settled fact. Now you are watching in real time as better data turns that bedrock into a question mark. No one expects foundational numbers to move this late in the mission, but absolutely no one anticipates that the revision would come from uncovering what was hiding under the cosmic floorboards. Before we get started on where this all leads, hold both maps in your mind at once. The old, clean diagram of a simple early universe and the new, messy JWST landscape. Feel the tension between them because in the next sections, that tension is going to stretch across cosmic time, the fate of the universe and what it means to live in a cosmos more crowded and more mysterious than it first appeared. Hold those two maps in your mind and now imagine this. What if both of them are being warped by a cosmic funhouse mirror? When astronomers say 2 trillion galaxies, that number sounds absolute, like a census. It is not. JWST does not sweep the whole sky, counting every island of stars. It stares at tiny keyholes in space, deep fields that cover areas smaller than a grain of sand held at arm's length, and scientists then extrapolate from those narrow pencil beams to the entire observable universe. Powerful, yes, but also dangerous. The expectation is simple. Sample a few regions, assume they are typical, scale up. The reality is harsher, cosmic structure is clumpy, galaxies cluster along filaments and voids like a vast foam, and rare objects can lurk in just a handful of sightlines. If one deep field happens to cut through a dense knot of early galaxies, the inferred population for the whole cosmos can explode. No one expects a few square arc minutes to decide the fate of cosmology. Yet that is the boundary JWST now walks. On top of that comes gravitational lensing, the universe's own optical trick. Massive foreground galaxies and clusters bend space-time, turning themselves into magnifying glasses for background light. A tiny, ordinary galaxy behind the lens can be stretched into arcs, split into multiple images, and brightened by factors of 10 or 100. To your eye, it looks enormous, brilliant, ancient. Underneath, it might be a modest system just boosted by curved space-time. This is where illusion turns precise. Lensing does not just magnify, it distorts. It can make galaxies appear larger than they are, shift their apparent positions, and smuggle faint objects over JWST's detection threshold. By the end of tonight, you're going to understand why some of the most dramatic early candidates sit right behind massive clusters in regions where the glass is thickest and the image the least trustworthy. Then there are selection effects, the quiet biases that shape every catalogue. Telescopes are drawn to the bright, the unobscured, the high-contrast beacons that punch through the cosmic fog. Dusty galaxies, low-surface brightness dwarfs, objects whose light has been scattered or stretched beyond a certain limit fall below the radar. The mission sees a universe of show-offs, not wallflowers. The result is a skewed portrait of the early solar neighborhood of the cosmos, where the loudest galaxies dominate the narrative. So here is the tension. Are JWST's shockingly bright, massive early galaxies genuine rebels, forcing a rewrite of Lambda CDM and the way dark matter scaffold structure? Or are we watching a carefully edited highlight reel amplified by lensing, biased by selection, and painted from a handful of tiny fields beyond which the true distribution remains hidden? Now, let's begin to peel back those illusions and see what remains when the mirrors are stripped away. Peel those mirrors back too fast, though, and something strange appears. The universe does not flatten out, it warps. Tonight, we're going to stand right in front of one of those warps, a massive galaxy cluster acting like a cosmic funhouse mirror. In ordinary space, light would travel in straight lines. Around a huge concentration of mass, space itself curves, and light follows the curve. The result is gravitational lensing, and for the James Webb Space Telescope, it is both a gift and a trap. Now, let's begin with the cleanest example. Picture a dense cluster of galaxies, hundreds of trillions of solar masses, sitting between you and a much more distant background galaxy. The cluster's gravity bends the background light. When the alignment is nearly perfect, the galaxy is stretched into bright arcs or even full rings. That's strong lensing. Dramatic distortions, multiple images, magnifications of tens or even hundreds. When the alignment is off-center, the effect softens. Background galaxies look slightly stretched, slightly skewed, their shapes subtly aligned. That quieter regime is weak lensing. For most of cosmic history, those lensed background galaxies would have been invisible, too faint, too far beyond any spacecraft's reach. But now, JWST stares through these clusters and the lens turns into a natural telescope. The cluster boosts the brightness of tiny, early galaxies that would sit far below JWST's normal detection threshold. The mission suddenly sees objects from a few 100 million years after the Big Bang that would otherwise be erased by distance and cosmic redshift. By the end of tonight, you're going to understand why that's dangerous. To turn those magnified smudges into real galaxy counts and real masses, scientists must undo the mirror. They build lensing maps of each cluster, using the distorted shapes of many background galaxies to reconstruct how mass, both visible and dark matter, is distributed. From that, they estimate the magnification of each image and divide the observed brightness by that factor. But every assumption about the cluster's mass adds uncertainty. Shift the dark matter slightly. Change the profile of the central galaxies. The inferred magnification, and therefore the true luminosity, can swing by factors of a few. Consider one dramatic case that raced through the community in JWST's first year. A galaxy apparently shining just 300, 400 million years after the Big Bang looked absurdly bright, with a stellar mass rivaling the Milky Way. No one expects a system that massive to assemble so quickly. No one predicts such a heavyweight so close to the cosmic dawn. Then the lensing models were refined. The magnification turned out to be higher than first thought. After correction, the galaxy shrank, still impressive, still challenging, but no longer an outright violation of Lambda CDM. So the funhouse mirror had exaggerated the rebel. The question is, how many other rebels are still hiding in the distortions, waiting for the next recalibration of the glass? So, the funhouse mirror had exaggerated the rebel. The question is, how many other rebels are still hiding in the distortions, waiting for the next recalibration of the glass? To answer that, the view has to zoom out from lensing arcs to something much more insidious, not a warped foreground cluster, a veil that's everywhere, interstellar dust. Tiny grains of carbon and silicate, smaller than smoke particles floating between stars and between galaxies. To human eyes it looks like emptiness, but to young, ultraviolet, bright stars, it's a wall. These grains are incredibly efficient at absorbing ultraviolet and visible light, swallowing the sharp blue glare of newborn star clusters and re-emitting that energy at longer, redder wavelengths. In optical and near-infrared images, whole regions of space can look quiet, even dead, when in reality they are blazing. That creates a second layer of illusion. A galaxy can be in the middle of a violent starburst, forming hundreds of solar masses of stars per year, and in Hubble, like wavelengths it barely registers. Designed to map the bright, clean universe, those surveys miss the dirtiest, most frantic construction sites. Dusty, starburst galaxies at high redshift can be among the most active systems in the cosmos, yet appear faint smudges or vanish entirely in the bands that built the original 2 trillion galaxy estimate. Now, let's begin to peel that veil back. JWST carries mid-infrared instruments that do not care if ultraviolet light has been absorbed. They look for the re-radiated glow, the warm whisper from those carbon and silicate grains. Where Hubble saw a dark patch, JWST sees orange and red knots, dust, enshrouded galaxies, compact and distant, lighting up in wavelengths that slip through the murk. By the end of tonight, you're going to understand why that single shift in wavelength turns empty sky into a construction zone. And JWST is not alone. Complementary observatories like ALMA tune in even longer wavelengths into the submillimeter regime, where cold dust shines most strongly. Together, they triangulate the hidden population. A faint smudge in JWST's mid-infrared becomes, in ALMA's view, a massive, dust-wrapped starburst only a few 100 million years after the Big Bang. No one expects the early universe to be this smoky. No one predicts that some of the most intense stellar factories would be nearly invisible in the very bands used to count galaxies. This is where the hidden layer gets complicated. The original 2 trillion figure leaned heavily on ultra-faint galaxies that Hubble could not see but models required. JWST is now hinting that part of that unseen population is not just faint, but buried in dust. Ultra-faint dwarfs, ultra-dusty starbursts, and everything in between may all be contributing to the missing light. The boundary between too dim to detect and too obscured to detect is blurring, and absolutely no one anticipates that simple galaxy counts will survive untouched. Tonight, we're going to follow that implication. If both ends of the population are hiding, what does that do to the total and to the story of how structure grew in the first place? So here's the deeper implication. If galaxies are hiding at both extremes, then the visible universe is not a random spray of lights on a black canvas. It's the illuminated skin of something larger. Tonight, we're going to peel that skin back and look at the framework underneath. Cosmologists call it the cosmic web. Imagine space not as empty, but as a 3-dimensional foam. Long filaments, dense nodes where filaments intersect, and vast, almost empty voids in between. That pattern is set not by ordinary atoms, but by dark matter collapsing under gravity, long before the first star ever switched on. The web is the skeleton. Normal matter is just the thin layer of muscle and light wrapped around it. Here's the critical trick. Dark matter does not shine. It doesn't emit, absorb, or reflect light in any way that present instruments can see, but it does pull. Wherever dark matter filaments concentrate, they deepen the gravitational wells in the young universe. Gas flows along those invisible ridges, cools, fragments, and ignites. Galaxies are not scattered wherever they please. They form along the filaments and pile up at the nodes. That means every galaxy is a tracer. Plot enough galaxies in 3 dimensions and an outline of the dark web emerges like frost, tracing the shape of an unseen window pane. Before the JWST, that map was sharp only for relatively nearby cosmic times when the universe was already a few billion years old. The earliest era was a blur with just a handful of faint points and a lot of guesswork connecting them. Now, let's begin. JWST's deep fields push that map back into the first few 100 million years after the Big Bang. In those tiny, empty patches of sky, the new spacecraft is not just seeing lone, isolated galaxies. Scientists are starting to see alignments, chains, clumps, proto-filaments that stretch across the field, where young galaxies already seem to prefer specific directions in space. In some fields, galaxies less than 400 million years old appear in elongated structures, hinting that the dark matter skeleton is already drawn in. The universe is barely out of its primordial fog, and yet the pattern looks suspiciously like a miniature version of the mature cosmic web seen billions of years later. No one expects that level of early organization. No one predicts such efficient clustering so soon. So here's the uncomfortable question. If galaxy formation is happening earlier and more efficiently than Lambda CDM timelines suggested, does that mean the dark matter web assembled faster too? Are the filaments thicker, denser, or more quickly sculpted than the standard model allowed? By the end of tonight, you're going to understand why that single possibility threatens to ripple through every calculation about structure growth, from the tiniest dwarf galaxies to the largest clusters anchoring the observable universe. Because if the scaffolding went up faster than planned, what else in the cosmic construction schedule is about to move? That's where the quiet phrase that runs modern cosmology steps onto the stage: Lambda CDM, the standard model of the universe, elegant, compact, and suddenly under pressure. Before we get started on the crisis, it helps to remember what this model actually says. Lambda is dark energy, the mysterious pressure that makes space itself accelerate outward. CDM is cold, dark matter, invisible mass that clumps under gravity and builds the cosmic scaffolding. In Lambda CDM, the universe expands, tiny ripples in the early plasma grow, and structure forms hierarchically. Small halos first, then bigger ones, then full, blown galaxies and clusters. In that picture, the early universe is supposed to be busy, but modest. A few small galaxies, dim, clumpy, still learning how to shine. Instead, JWST stares back to a few 100 million years after the Big Bang and finds something that looks ahead of schedule. Galaxies that are brighter, more massive, and more numerous than many Lambda CDM-based simulations predicted at those redshifts. It's like walking into a construction site at dawn and seeing skyscrapers already lit up. No one expects the standard model to crumble because of a single surprising galaxy. But JWST is not handing over a single object, it is delivering populations. Candidate galaxies at redshift 10, 12, even beyond, with stellar masses and star formation rates that, on paper, push against how fast gravity and gas are allowed to work in this framework. The tension is not that Lambda CDM predicts nothing there. It's that the balance of what is there, the numbers, the luminosities, the apparent masses, sometimes seems too bold for such an early cosmic morning. Now, let's begin to pull apart what that really means. Every prediction from a simulation sits on a pile of assumptions. How efficiently does gas turn into stars? How quickly do supernovae and black holes blow that gas back out, throttling growth? How clumpy is the initial dark matter web that threads through space? Tweak star, formation efficiency upward, weaken feedback, or adjust the initial power spectrum within observational limits, and galaxies can grow faster without breaking the entire solar, 2. Galactic system of physics. That's why most scientists are not throwing Lambda CDM out the airlock. Not yet. They are testing it. They are asking whether the mismatch is statistical noise in small samples, astrophysical complexity in how galaxies light up their dark halos, or a truly fundamental crack in the way dark matter and dark energy are modelled. No one predicts that all three answers will agree. Tonight, we're going to follow that conflict between theory and observation as it sharpens. Because the next question is ruthless. Are we just misreading the light, or is the invisible scaffolding itself about to change? So, if the invisible scaffolding might be wrong, there's another possibility that is just as unsettling. Maybe the universe did not take the slow, careful route that every simulation assumed. Maybe galaxies fast tracked their way into existence. Now, let's begin with the most conservative rebellion. In the standard picture, dark matter halos form first, then gas falls in, cools, and very gradually turns into stars. The expectation is a cosmic drizzle. JWST is seeing something closer to a downpour. One way to get that: make the gas lose energy more efficiently so it can collapse faster into the centers of those halos. In the early universe, the gas is nearly pristine hydrogen and helium. No heavy elements, no dust, none of the usual coolants that help gas radiate away heat in the modern solar neighborhood. The prediction is that this should slow star formation. But the light JWST sees suggests the opposite. Extremely dense regions where star formation seems to be running near maximum efficiency, converting a huge fraction of gas into stars in just a few 100 million years. Scientists are now asking whether turbulence, strong radiation backgrounds, or even the streaming motion between dark matter and gas right after the Big Bang could have created pockets where cooling was much more effective than anyone expected. The boundary between too hot to collapse and cold enough to form stars might have been crossed far earlier and far more violently than the calm equations implied. Then there is the second lever, not just how fast stars form, but what kind of stars form. By the end of tonight, you're going to understand why that matters. Modern galaxies form stars with a wide range of masses, from tiny red dwarfs to blue giants, but most of the mass ends up in small, faint stars. This distribution is called the initial mass function. Change that distribution and the universe changes with it. If the early initial mass function was top-heavy, favoring very massive stars, a young galaxy could look absurdly bright, without actually containing as much total mass. A few thousand stars each, dozens or hundreds of times the sun's mass pour out ultraviolet light, explode as supernovae, and flood space with heavy elements. To JWST, that galaxy looks old and huge. Under the hood, it might be a luminous but short, lived flare. No one expects the conservative options to stop there. Some scientists push further, into ideas that sound like science fiction but are carefully modelled. What if dark matter itself clumped earlier and more strongly, creating over-dense regions that acted like gravitational traps for gas? What if primordial black holes formed in the first fractions of a second served as seeds, pulling in matter and building galaxies around them long before normal processes would allow? What if gravity on very large scales is not quite Newtonian, not quite Einsteinian, but slightly enhanced in ways that make collapse easier in the young cosmos? Each of those scenarios rewrites a different part of the mission plan for structure formation. Earlier dark matter clumping changes how halos merge. Primordial black holes add bright accretion disks and early jets. Modified gravity alters the timing of when the cosmic web thickens. And absolutely no one anticipates that they would all leave identical skies. That is the crucial advantage. Every fast-track idea leaves fingerprints. A top-heavy initial mass function leaves chemical patterns in the gas between galaxies. Hyper-efficient cooling leaves compact, dense star clusters. Early black holes leave X-ray backgrounds and distorted galaxy shapes. Modified gravity changes how galaxy motions trace mass. JWST can already probe some of those signatures in the infrared. Future X-ray missions, 21 centimeter radio surveys, and even gravitational wave detectors will probe others. Tonight, we're going to follow those fingerprints across cosmic time. Because the next question is even sharper. What if the hidden layer is not just faster, but fundamentally different in how it builds light from darkness? So let's rewind the clock on the whole 2 trillion galaxies headline, because that number did not fall out of the sky. It came from one of the boldest extrapolations in modern astronomy. Take a tiny keyhole of space, stare at it for weeks with Hubble, and then scale that microscopic sample to the entire observable universe. Now, let's begin. The original Hubble Ultra Deep Field looked at an area of sky so small that held at arm's length it was a speck on your thumbnail. In that speck, scientists discovered thousands of galaxies, many so faint they were just a handful of photons over many days. Then, they did the dangerous thing. They modelled how many even fainter galaxies must exist beyond Hubble's detection limit, extended that luminosity function to lower and lower brightness, and multiplied by the whole cosmic volume. The result? Roughly 2 trillion galaxies within the observable boundary. Expectation: the universe is teeming with tiny, dim galaxies, invisible to our best optical eyes. Reality, once JWST enters the mission, is more complicated. When Webb looks back to certain redshifts, especially in the first few 100 million years, it sees fewer small, ultra-faint galaxies than those extrapolations predicted. The low-mass end of the galaxy population seems to bend down. That hints that the total count might actually be lower than 2 trillion. This is the prediction versus observation moment. Models said there should be a steep rise in the number of puny galaxies as you go fainter. JWST's infrared vision, sensitive to redshifted starlight and the glow of early dust, is not finding as many of those as expected in some epochs. No one predicts that the most powerful space telescope ever launched might reduce the census of galaxies. But before we get started on erasing half the universe, there is a twist. JWST is also unveiling entire populations that were missing from Hubble's view. Ultra-dusty galaxies wrapped in thick cocoons that block visible light now blaze in the infrared. Ultra-faint systems magnified by gravitational lensing suddenly appear when a foreground cluster acts as a natural cosmic telescope, and compact, red, high redshift candidates sitting right at the edge of detectability are adding light where there was only darkness. So the count shifts in both directions. Fewer of some kinds of small galaxies, more of the hidden, dusty, and lensed ones. Tonight, we're going to use that tension as a clue. Because by the end of tonight, you're going to understand that the raw tally, 1 trillion, 2 trillion, 10 trillion, is not the real prize. What matters is how mass, light, and structure are distributed across cosmic time, how dark matter scaffolding channels gas, how the first stars ignite and blow winds through the young cosmic web. The precise final number of galaxies will move as JWST and future missions refine the census. And absolutely no one anticipates that this question stays settled for long. So the universe may host fewer galaxies than the headline number, or more, or just differently arranged. The real mystery is what that arrangement is telling us about the hidden layer itself. So the universe may host fewer galaxies, or more, or just differently arranged. Now let's begin to ask what that arrangement actually means, because this hidden layer is not just extra dots on a map, it is a time machine. Every faint, distant galaxy JWST pulls out of the dark is a frozen moment, a specific chapter in the universe's early history. Light leaves those systems when the cosmos is only a few 100 million years old, then spends over 13 billion years crossing intergalactic space to reach a single mirror in a single spacecraft parked beyond the moon. Think of the field of view as a bookshelf. Nearby galaxies are the recent volumes, thick with spiral arms and heavy elements. Farther out, the books get thinner, rougher, written in a younger, cosmic language. By the end of tonight, you're going to understand that when astronomers talk about redshift, they are really talking about which shelf the telescope is reading from in this universal library. Redshift stretches the light, pushing it from visible into the infrared. That is where JWST lives. By sampling thousands of galaxies at different redshifts, scientists reconstruct a timeline. When the first stars ignited, how quickly galaxies assembled, when heavy elements like carbon and oxygen flooded the gas between systems, and how the invisible dark matter scaffolding pulled everything into the cosmic web. Expectation, a slow, gentle dawn. Reality, a rapid, crowded, turbulent sunrise. But those galaxies start as smudges, tiny, dim patches of light. Hubble could see some of them, but it could not read them. No one expects a smear a few pixels across to reveal an entire internal history. JWST changes that with spectroscopy. It splits that faint glow into hundreds of colors, revealing fingerprints of hydrogen, helium, oxygen, even the imprint of dust grains swirling in early galactic winds. From those fingerprints, astronomers measure ages, metallicities, dust content, and ionizing output. How old are the stars? How enriched is the gas? How much ultraviolet light is pouring out to rip electrons off hydrogen and finish rionizing the universe? These are not abstract questions. They tell whether a galaxy is a newborn starburst, a surprisingly mature system, or something that absolutely no one anticipates at that epoch. Hubble's deep fields gave the table of contents. JWST's hidden layer is the missing pages, the scribbles in the margins, the corrections to the first draft of cosmic history. Before we get started on what those corrections actually say about our cosmological model, there is one more twist. The earliest chapters are not just hard to read. Some may be actively erased by dust and distance, and that means the diary might still be hiding even deeper secrets than this first hidden layer reveals. Those erased lines are not just missing anecdotes, they might be the fingerprints of the event that turned a foggy universe into a transparent one. Now, let's begin with the big transition. For the first few 100 million years, space is filled with neutral hydrogen. Photons scatter, bounce and get trapped. The cosmos is bright on the inside, but from the outside, it looks like a closed curtain. Rionization is the moment that curtain burns away, when ultraviolet light from the first sources strips electrons off hydrogen and leaves the intergalactic medium ionized, clear, and open. By the end of tonight, you're going to understand why this isn't just a background process. It is the change in state that lets galaxies, planets, and eventually entire solar systems see each other across cosmic distances. It is the moment when the universe stops hiding its own structure. The early models are simple. A few bright galaxies, maybe some quasars, pour out intense ultraviolet radiation. Their photons march outward, carve growing bubbles of ionized gas, and eventually those bubbles overlap. Problem solved. But when scientists actually count the photons from the brightest visible galaxies, something doesn't add up. The math comes up short. There are not enough ionizing photons to finish the job on schedule. No one expects the heroes of rionization to be almost invisible, yet that is exactly what JWST is hinting at. Ultra-faint galaxies, too small and too dusty for Hubble to register, may be doing most of the work. Individually, they are weak. Collectively, they are a flood, a hidden layer of tiny, star-forming systems that leak ultraviolet light into the cosmic fog, one ion at a time. How do you find such ghosts? JWST does not just take pretty pictures, it dissects light. It looks for Lyman alpha, a specific ultraviolet transition of hydrogen that gets stretched into the infrared by cosmic expansion. When that line is missing or distorted, when there is a broad, damping wing carved into the spectrum, it means neutral hydrogen is still lurking around the galaxy, swallowing those photons. This is where the pattern interrupt hits. Some galaxies at the same cosmic time show strong Lyman alpha lines shining through clear, ionized channels. Others are muffled, wrapped in neutral gas. The boundary between ionized and neutral is not a smooth shell. It is a patchwork. The emerging picture is dramatic. Rionization is not a quick, uniform flash. It is an extended, uneven process, driven from below by a vast sea of faint galaxies that absolutely no one anticipates in such numbers. Bright galaxies sketch the outlines, but the ultra-faint population fills in the page, punching countless small holes in the fog until the whole medium gives way. In other words, the hidden layer is not just extra galaxies, it is the engine that rewrites the physical state of space itself. And if reionization is this patchy and prolonged, then another assumption about the early universe is about to be challenged next. If that hidden layer can reshape the state of space itself, the next question is obvious. How do you actually map it? Now let's begin. Because the telescopes flying today are only the first scouts, the real cartographers of this buried cosmic web are lining up on the launch pad and on mountaintops, and they are designed to do something JWST alone cannot: turn a handful of spectacular snapshots into a full-scale survey of the universe. JWST is a scalpel, tiny field of view, extreme depth. It stares at a patch of sky the size of a grain of sand at arm's length and pulls out galaxies from 300 million years after the Big Bang. That's how the hidden layer was discovered in the first place. But to understand how common those galaxies are, how they cluster, how they evolve, you also need a wide net. Enter the Nancy Grace Roman Space Telescope and Euclid. Roman will fly with a camera that, in a single exposure, can cover an area of sky about 100 times larger than JWST, while still reaching back billions of years. Euclid is already in space, mapping huge swaths of the cosmos to trace dark matter through weak gravitational lensing. Together, they trade some of JWST's depth for sheer scale, turning the narrow tunnel into a panoramic window. Combine them, and a new kind of cosmic archaeology appears. Deep JWST pointings anchor the timeline, showing the detailed structure of galaxies in the hidden layer. Wide Roman and Euclid surveys provide the statistics: how many galaxies per unit volume, how strongly they cluster, how their properties change with cosmic time. Expectation, isolated curiosities that can be explained away. Reality, a full census that either slides smoothly into Lambda CDM or refuses to fit. By the end of tonight, you're going to understand why that combination is so dangerous for a theory. When you know both the fine-grained structure and the large-scale pattern, there is nowhere for a flawed model to hide. The number of galaxies, their masses, their star formation rates, their alignment with the dark matter scaffolding, all of it becomes a stress test for the entire cosmological system, and that's just in space. On the ground, a new generation of 30-meter class telescopes, the extremely large telescope in Chile, the 30-meter telescope, and the giant Magellan telescope, if their missions proceed, will turn those faint JWST smudges into spectra. Each spectrum is a barcode of elements, motions, and temperatures. High-resolution spectroscopy will reveal how fast gas is flowing, how metals enriched the early universe, and whether the solar abundance patterns seen today were already locked in when those first galaxies lit up. No one expects all three fronts, deep, wide, and high resolution, to agree perfectly with the current Lambda CDM picture. No one predicts every boundary condition will line up neatly once the error bars shrink. And absolutely no one anticipates what happens if Roman, Euclid, JWST, and the 30-meter giants all point to the same uncomfortable conclusion. Because that is when the hidden layer stops being a curiosity and becomes a verdict. In the next section, the question shifts from "what did we discover?" to "what has to change if the universe refuses to obey?" So, what happens when that verdict arrives and the maps do not match? When the universe on the screen refuses to look like the universe in the simulation? That is where the hidden layer stops being poetic and starts being a problem. Now, let's begin with the digital universes that scientists have already built. Massive cosmological runs like Illustris TNG and Eagle start with a nearly uniform sea of dark matter and gas, then let gravity, expansion and physics turn that sea into galaxies. Over billions of simulated years, the dark matter collapses into filaments, gas falls into those wells, stars ignite, black holes grow, and feedback from explosions and jets blows material back out into space. These are not toy models. They fill cubes of space hundreds of millions of light years across, with tens of billions of particles. They produce spiral and elliptical galaxies, galaxy clusters, and cosmic Webb filaments that look eerily like what real telescopes see. By the end of tonight, you're going to understand that in the standard picture, these simulations are the bridge between a simple early universe and the complexity seen today. Crucially, they do more than draw pretty images. They predict how many galaxies of each brightness should exist at each epoch, the so-called luminosity function. They forecast how stellar mass is distributed, how big galaxies should be, how chaotic their shapes are, and how quickly stars should form when the universe is only a few 100 million years old. Those curves and histograms were in place before JWST ever left the ground. Then JWST looked back to that era, and the head-to-head comparison began. Expectation at redshifts 10, 12, 13. There should be a steep drop in bright galaxies because there simply has not been enough time to pile up that much mass. Reality. JWST finds candidates that are small in physical size but astonishingly bright, with stellar masses and star formation rates that push right up against, and sometimes beyond, those simulation lines. The boundary was supposed to be clean, a gentle tapering of light toward the cosmic dawn. Instead, the bright end of the luminosity function looks overpopulated. Some galaxies appear too compact, others already show disks or clumps that resemble mature systems. No one predicts skyscraper-level galaxies in what should still be a village of cosmic huts. So the simulators go back to work. They rerun universes with stronger or weaker feedback from supernovae and black holes because feedback controls how fast gas cools and turns into stars. They tweak star formation recipes, allowing dense gas to ignite more efficiently. They push to higher resolution so that small, turbulent clouds are not washed out numerically. No one expects a single dial to fix it. Instead, entire teams are racing to chase JWST's reality. And even after all that, a gap remains. Some updated runs get closer, some overshoot in other ways, but the perfect overlay of theory and telescope still refuses to appear. In the next section, that unresolved gap stops being a technical nuisance and becomes a suspect, forcing scientists to ask whether the hidden layer lies in the galaxies themselves, or in the laws used to grow them. That's the moment the galaxy census stops being a head count and turns into a stress test. Because how many galaxies appear at each mass at each redshift is not just trivia. It is a direct measurement of how fast structure grows in space. Now, Let's begin. In the standard Lambda CDM picture, dark matter collapses first, forming an invisible scaffolding. Gas falls in, stars ignite, galaxies light up. The rate at which small clumps merge into big halos is locked to two things: how cold and collisionless the dark matter is, and how strongly dark energy pushes back on gravity as the solar system's universe expands. So, when JWST reports too many big galaxies too early, or too few faint ones where simulations expected a swarm, that is not a cosmetic disagreement. That is the growth curve of the cosmos bending away from the textbook. If small halos are missing, warm dark matter that erases tiny structures starts to look tempting. If massive galaxies appear far ahead of schedule, self-interacting dark matter that redistributes mass, or a dark energy term that changes strength with time, suddenly moves from theory paper to suspect list. By the end of tonight, you're going to understand why this hidden layer of galaxies is really a hidden layer of equations. The number of halos of a given mass at a given redshift is predicted precisely by Lambda CDM. Change the dark matter from cold to warm, and lo, mass galaxies evaporate from the early record. Add strong self-interactions and central densities flatten, changing how galaxies lens background light. Let dark energy evolve, and the entire timeline of when clusters and filaments appear shifts. But galaxy counts do not live alone. They plug into a wider system of cosmic probes. The cosmic microwave background freezes in the initial conditions, the tiny ripples in density that later became planets, stars, and galaxies. Baryon acoustic oscillations trace how those ripples stretched as the universe expanded. Gravitational lensing maps how all the mass, luminous and dark, actually ended up distributed between us and those distant galaxies. Before we get started on exotic new physics, scientists force all of these to talk to each other. The CMB sets the starting line, BO and supernovae pin down the expansion history. Lensing reveals the present, day Webb. Then JWST's galaxy statistics fill in the middle chapters, from the first few 100 million years to more recent cosmic times. If one ingredient in the model is wrong, the story breaks somewhere. No one predicts it will break in a way that leaves galaxy counts untouched. That is why the hidden layer matters. It is not just extra scenery beyond the bright, familiar galaxies. It is a precision tool, a lever on dark matter's temperature, on whether dark energy is a simple constant or a changing field, on whether the whole Lambda CDM mission profile survives contact with the real universe. And if those levers all start pointing in the same strange direction, the next section is where the foundations of cosmology begin to move. Those foundations do not move by themselves. They move because people, very human people, are staring at screens at 2 a.m., arguing over whether the universe has just broken their favorite equation. The first, JWST deep fields drop, and within hours the private Slack channels and late-night Zoom calls ignite. Tiny red smudges at the edge of vision, galaxies that, on paper, should not exist that early. Designed to tidy up the Lambda CDM mission profile, this spacecraft suddenly looks like it has discovered a crack in the hull. No one expects that from the calibration phase. Some teams rush to publish. Photometric redshifts say these objects live less than 400 million years after the Big Bang, yet they shine like mature systems. They seem too bright, too massive, too well organized. It is the skyscraper in A. Stone, Age Village problem now rendered in infrared. By the end of tonight, you're going to understand that before the headlines appear, there is a storm of second guessing behind the scenes. Across the world, other groups take the same raw data and refuse to trust it at face value. They rebuild the pipelines from scratch, they check detector noise flat, fields, cosmic ray hits. They argue over which galaxies are really at extreme redshift and which are dusty imposters closer in. One paper revises masses downward. Another adjusts the light profiles. A third says the redshifts might be lower. The boundary between impossible galaxy and ordinary outlier shifts week by week. This is where the emotional tension lives. Some scientists quietly hope for new physics. Others almost dread it, because new physics means years of hard work rebuilding the solar system of cosmology from the ground up. Skepticism collides with wonder. A senior researcher tells a student, check the photometry again for the 5th time, not because they want the galaxy to go away, but because if it stays, the story of structure formation has to change. Now, let's begin to see the pattern. One camp tunes the models. Maybe star formation was more efficient, maybe dark matter cooled faster, maybe feedback winds behaved differently in dense early halos. Another camp asks if Lambda CDM itself is missing a hidden layer, some subtle ingredient that only shows up when the universe is a few 100 million years old. Before we get started on dramatic conclusions, this is the triumph that matters. Independent teams competing, checking, failing to agree, then converging. The process is messy, but it is how space science self corrects, how a 2 trillion galaxy estimate can be challenged without the whole system collapsing into chaos. Whether these galaxies tame themselves inside refined models or force a rewrite of the script, the curiosity and rigor on display are already the real discovery. And if, after all the recalibrations and retractions, the anomalies refuse to vanish, the next step is unavoidable. The community has to ask whether the hidden layer beneath those galaxies is pointing to a deeper rewrite of cosmic history. When a hidden layer appears under 2 trillion galaxies, it does something strange to the human mind. It is not just a new data point. It is a reminder that the universe is not finished teaching, and that every time we think the picture is complete, the frame peels back to reveal more space beyond. This has happened before. In biology, cells looked like simple blobs until microscopes sharpened and revealed organelles, DNA, entire molecular machines humming beneath the surface. In geology, continents were fixed islands of rock until plate tectonics exposed a moving, convecting interior. In physics, atoms were indivisible beads until quantum theory cracked them open. Each time the pattern is the same: expectation on top, deeper structure underneath, and a sudden expansion of what it means to understand the system. Now, let's begin to see JWST as part of that same long pattern. 2 trillion galaxies sounded final, a census, a line in the textbook. But as soon as scientists used a colder mirror and longer wavelengths to look past the glare and the dust, a hidden scaffolding of ultra-faint galaxies and dark matter emerged where models had predicted smoothness. The message is quiet, but unmistakable. Even the most precise number is provisional when the boundary of observation moves. Tonight, we're going to treat that provisional quality not as a weakness of science, but as its core strength. The mission is never to freeze the map. It is to keep sending better spacecraft, better telescopes, better theories into regions where no one expects surprises to survive. No one predicts that a patch of sky that looked nearly empty will erupt with ancient galaxies when viewed in infrared. And absolutely no one anticipates that those galaxies will be too massive, too bright, and too common for the reigning model to explain cleanly. That uncertainty loops back to a very local question. How typical is the Milky Way, really? In a universe with hundreds of billions or trillions, or some yet uncounted swarm of galaxies, the solar system feels both tiny and strangely privileged. The planets orbit a quiet star in an ordinary spiral arm, yet life has arisen here, and at least one technological civilization is building instruments that can measure the wind of the early universe. Does a richer, hidden layer of galaxies make life more common? Because there are more habitats, more experiments in chemistry and time? Or does it emphasize how hard it is to be noticed, even in a cosmos overflowing with worlds? By the end of tonight, you're going to understand that the numbers alone cannot answer that. What they can do is stretch the range of what feels plausible. If there was a concealed layer beneath 2 trillion galaxies, what else might be waiting just beyond our current horizon? Another population of objects so faint that even JWST only hints at them? A different phase of cosmic evolution hidden in neutrinos or gravitational waves rather than light? The original plan is simple. Count galaxies, refine models, converge on a single clean story. The reality is stranger. Each new layer exposes more questions than it resolves, and the most unsettling, exhilarating possibility is that the universe is layered all the way down. So if the universe is layered all the way down, where does it stop? At what point does even a telescope like JWST run into a wall it can never cross? To answer that, you have to zoom out beyond instruments, beyond engineering, all the way out to the structure of space and time themselves. There is a hard boundary built into the cosmos, not a metal shell, not a ring of planets, but a horizon in time. Light has a finite speed. The universe has a finite age. Combine those, and there is a maximum distance light can have travelled since the Big Bang. Beyond that, no signal has ever had time to reach us. Cosmologists call one version of this limit the surface of last scattering. About 380,000 years after the Big Bang, the plasma cooled enough for atoms to form, and space suddenly became transparent. The cosmic microwave background is the fossil light from that moment. JWST can see back to a few 100 million years after the beginning, into the era when the first galaxies lit up. But it can never see past that opaque wall. No one predicts a future telescope that just sees around it. That boundary is written into the physics. Tonight, we're going to stand right at that edge and then lean over it. Because inflationary models say the story doesn't end where the light stops. In many versions of cosmic inflation, the tiny patch that became our observable universe is just one bubble in a vastly larger inflating space. Beyond our horizon, inflation may have continued, spawning region after region, each with its own arrangement of matter, its own cosmic web, possibly even slightly different values for the same physical constants. From inside one bubble, these other regions are forever hidden. No spacecraft can cross that gulf, no radio signal can bridge it. The expansion of space outruns every messenger. Yet the equations that describe the early universe almost demand that something lies beyond our visible boundary, the way the wind at the edge of the heliosphere demands an interstellar medium outside the solar system. Now, let's begin to connect that to JWST. The hidden layer it revealed beneath the 2 trillion galaxy picture might not be the bottom of the cosmic hierarchy. It may be the innermost shell of a nesting structure, bright galaxies on top of ultra-faint ones, all riding on dark matter scaffolding, all embedded in a larger inflating space we can never see. Each time scientists thought the mission was complete, a deeper layer appeared. By the end of tonight, you're going to understand how far this map can be pushed and where every map must end. Because in the next sections the story leaves light behind. The question becomes, when telescopes reach their final horizon, what else is left to probe the regions beyond? So the map has an edge. Light runs out. Telescopes hit a wall. But before that boundary there's another surprise. The universe's population count is changing. For years the headline number was almost mythic. About 2 trillion galaxies in the observable universe. That wasn't measured one by one. It came from a clever extrapolation. Hubble stared at tiny, empty-looking patches of space for hundreds of hours, building those famous deep fields where every speck of light became a distant island of stars. Then scientists took the galaxies Hubble could see, modelled how brightness should drop off towards smaller, dimmer systems, and extended the curve far beyond its detection limit. Expectation? Beneath Hubble's reach there should be a vast swarm of ultra-faint dwarf galaxies. Reality? That swarm is exactly what the James Webb Space Telescope was built to test. JWST sees in infrared the stretched, reddened light of the early universe. It can pierce through dust that hid galaxies from Hubble, and it can pick up galaxies that formed just a few 100 million years after the Big Bang. Before we get started on the wild implications, focus on one quiet result. In some of the deepest JWST fields at certain epochs, there are fewer of the tiniest, faintest galaxies than those Hubble-based models predicted. Not none, just fewer. The faint end of the galaxy population curve doesn't rise as steeply. That single change ripples outward. When the curve is shallower, the total number of distinct galaxies in the observable universe drops. Not by a factor of 10, but enough that the famous 2 trillion estimate may be an overcount. No one expects that headline to get smaller and the universe to become more complicated at the same time. Yet that's exactly what the data are saying. Fewer galaxies does not mean a simpler cosmos. It means that, on average, galaxies are brighter, more massive, and more efficient at turning gas into stars than standard models of structure formation assumed. The early universe is not a quiet nursery of fragile star clusters. It looks more like a construction zone running at full tilt. This is the pattern that keeps repeating. The count goes down, but the intensity goes up. The galaxies JWST does see at high redshift often look too luminous, too mature, too quickly assembled. No one predicts skyscraper-scale systems rising in what should still be a cosmic village. Tonight, we're going to reframe what that means. The hidden layer here is not just a missing line on a census form. It is the underlying architecture, the dark matter scaffolding that gathers gas, the flows of light and heavy elements through that web, the way star formation ignites along invisible filaments like sparks, tracing a magnetic field. By the end of tonight, you're going to understand why the real question is no longer how many galaxies exist, but how is matter arranged beneath them? Because JWST is starting to reveal that the universe is less crowded than advertised, yet woven together far more tightly than anyone anticipated. The public story is simple. JWST is just a sharper Hubble, a high-definition upgrade pointed at the same universe. But that picture is wrong. JWST is not just seeing more, it is tuned to a different layer of reality. Hubble lives mostly in visible and ultraviolet light, the same slice your eyes use. JWST was built for the glow that has been stretched by cosmic expansion light that left the first galaxies as searing ultraviolet and arrived here 13 billion years later as faint, cold infrared. When JWST stares into space, it is not just looking farther, it is watching time itself redshift into a new spectrum. Before we get started, it helps to remember what that means. A photon that left a newborn galaxy 300 million years after the Big Bang has been riding the expanding fabric of the cosmos ever since. Its wavelength has been pulled, elongated, by a factor of 10 or more. Hubble loses it. JWST's mirrors and detectors are tuned precisely to catch it, but JWST does not send back a raw photograph. Its instruments count individual infrared photons at wavelengths your eyes will never see. Then scientists assign those wavelengths to colors and combine multiple filters. The famous JWST images are not postcards. They are carefully reconstructed maps of temperature, chemistry, and structure from an epoch that would look utterly alien to any human observer. And that alien epoch is not behaving. The standard Lambda CDM model predicted a young universe filled with small, ragged, dim galaxies slowly assembling inside dark matter halos. Instead, JWST keeps finding objects that are too bright, too massive, and too well organized far too early. Spiral, like disks where there should be chaotic clumps. Star factories pumping out light at rates that strain every timeline. No one expects to see heavy elements and thick dust so soon after the first stars ignite. Yet spectra from some of these early galaxies show oxygen, carbon, even complex dust grains that usually take multiple generations of stellar death to build. The universe is supposed to be pristine at this stage. JWST is catching it already recycled. This is where the hidden layer emerges. These images are not just adding more galaxies to a census. They are exposing how the invisible cosmic web, the dark matter scaffolding, and the feedback from the first stars and black holes carved channels into space, funneled gas, and lit up specific nodes while leaving others strangely empty. Tonight, we're going to treat each bright galaxy as a tracer, a die dropped into a three-dimensional flow. By the end of tonight, you're going to understand that JWST is less a camera and more a tomography machine for the universe, slicing through time to reveal how the underlying web bends, redirects, and sometimes chokes off the solar system scale rivers of matter that feed galaxies. No one predicts what happens when those hidden currents collide. That is where JWST's next surprises are waiting, just beyond the glowing surfaces we can see. Those hidden currents are not just abstract lines in a simulation, they are the framework for an entire buried universe. Tonight, we're going to peel back that layer and give it a shape you can hold in your mind. Picture the hidden layer as a three-part structure. First, scattered along the dark matter web are tiny, ultra-faint galaxies, compact islands of stars, so small and so dim that Hubble barely registered a whisper from them. They are the cosmic back alleys, not the bright downtowns, packed with young stars, crowded into tight knots. They live deep in the gravitational wells carved by invisible matter. Second, running through and around them are the filaments themselves. Long, cold rivers of dark matter threading space like a three-dimensional nervous system. Galaxies, even the faintest ones, are not sprinkled randomly. They sit on this scaffolding, like dew on a spider web at dawn. The web sets the boundary lines. It decides where gas can fall in, where stars can ignite, and where whole clusters of galaxies will eventually form. Third, wrapping over all of this is the smoke. Veils of microscopic dust grains forged in the first generations of stars and supernovae, absorbing starlight and re-emitting it as a dull infrared glow. To visible light telescopes, that smoke is a blindfold. It erases entire galaxies from the record, turning rich, star-forming regions into apparent voids. Now, let's begin to map it. JWST sees the buried fire itself, The infrared light from newborn stars inside these dusty, compact galaxies less than a few 100 million years after the Big Bang. Gravitational lensing, where massive galaxy clusters bend space like a glass lens, magnifies the ultra-faint galaxies riding the dark filaments behind them, turning otherwise impossible targets into detectable smudges, and submillimeter observatories tuned to even longer wavelengths trace the cold glow of the dust, drawing in the outlines of the smoke that hides everything else. Each technique is blind to part of the picture. Together, they turn into a tomography mission for the entire cosmic web. JWST sketches the star-forming cores, lensing sketches the underlying dark framework. Submillimeter maps sketch the dust that reroutes the light. Layer those views, and the hidden cake under the bright frosting finally comes into focus. By the end of tonight, you're going to understand that most stars may have formed down there, not in the showy, well-lit galaxies that dominate pretty images, but in cramped, dust-choked systems buried in dark matter wells. No one expects the glamorous surface to be the minority report, yet that is what the data are saying. The visible universe, the part that looks complete in a Hubble deep field, is just the frosting on top, thin, bright, and misleading. Underneath is a dense, intricate cake of ultra-faint galaxies, dark filaments, and cosmic smoke, holding most of the structure and most of the history. And absolutely no one anticipates how different the recipe for that cake might be from the standard cosmological model. So, does that hidden cake mean the recipe of the universe is wrong or just incomplete? To answer that, you need one clear picture of what the current recipe really is. In the standard cosmological model Lambda CDM, the universe is not built from the bright things you see. It is a dark ocean dominated by dark energy and cold, dark matter, with normal matter floating on top like a thin, glowing film. Galaxies, stars, planets, every solar system are tiny ripples on a sea whose true depth is invisible. Dark matter provides the scaffolding. Dark energy drives the long-term expansion. Ordinary atoms just trace the pattern. Under that framework, scientists can run a mission on a supercomputer. Start with a nearly smooth universe, add quantum seeds, let gravity and dark matter pull, let gas cool and ignite. Out come galaxies, small ones first, then mergers, then the majestic spirals and giant ellipticals that Hubble discovered. The match to large, scale structure, to the cosmic microwave background, to the expansion history is astonishing. But when JWST looked back to the first few 100 million years, the prediction versus observation pattern shifted. The simplest Lambda CDM-based galaxy formation models expected tiny, dim building blocks. Instead, the spacecraft is seeing early galaxies that are bright, massive, and already enriched with heavy elements. Some candidates less than 400 million years after the Big Bang look as if they contain as many stars as a present-day Milky Way. No one expects skyscrapers in a Stone Age village. That does not immediately break Lambda CDM itself. It bends the assumptions layered on top. The tension is not with the dark ocean, but with how that thin film of light is forming waves. Are stars forming more efficiently than thought? Are black holes growing faster, pumping energy and metals through young systems? Or are redshifts and masses being misestimated by light warped through dust and complex spectra? Tonight, we're going to follow how scientists are testing the model. They are refining simulations, adding more realistic feedback from exploding stars and ravenous black holes, letting radiation, winds, and outflows blast through early galaxies. They are exploring dark matter that is not perfectly cold, that might be slightly warm or interacting, changing how quickly small clumps merge. They are hunting for observational biases, selection effects, and subtle calibration errors that could make rare outliers look common. By the end of tonight, you're going to understand why no one predicts a single JWST data release to overthrow decades of cosmology. But absolutely no one anticipates that a model under this much pressure will emerge unchanged. We are not yet at the point of throwing out Lambda CDM. We are very much at the point of bending it, poking it, and asking whether the hidden layer JWST is revealing is a warning sign of a deeper overhaul still to come. Now, let's begin to peel that layer back and see what, exactly, might need to evolve. Now, let's begin to peel that layer back in the most personal way possible. Because the hidden galaxies JWST is dragging out of the dark are not just curiosities at the edge of time. They are ancestors. The heavy elements in your blood, in your bones, in the device you're watching this on, were forged in stars that lived and died in structures like these. Those first galaxies are not polished spirals. They are turbulent, compact engines slamming gas together, lighting up new stars, and then tearing them apart with radiation and supernova shockwaves. Each explosion hurls carbon, oxygen, iron into surrounding space. Over billions of years, that enriched gas falls into new galaxies, forms new generations of stars, and eventually condenses into planets. Draw a straight line from a hyperactive, dust-choked galaxy 13.3 billion light years away to calcium in your teeth. That is what scientists are quietly doing when they trace chemical abundances across cosmic time. Tonight, we're going to stand back and look at the scale of that story. Whether the final tally is 2 trillion galaxies or only a few hundred billion, the universe is still almost incomprehensibly vast. That part does not change. What does change is the tempo. JWST is showing that the early universe was not a slow, tentative dawn. It was a crowded, high-pressure city of light where galaxies grew faster, merged more often, and exchanged material more efficiently than models predicted. Expectation versus reality again. Expectation, a simple, mostly empty cosmos gradually assembling structure. Reality, an intense, interconnected network where gravity, dark matter, and radiation cooperate to build stars and planets far earlier than anyone thought the standard model allowed. By the end of tonight, you're going to understand that hidden layer is not just about missing galaxies. It is about a different rhythm for the entire system. There is a philosophical impact here that is hard to ignore. You live in a cosmos that hides most of its structure in darkness and dust. Dark matter halos with no direct glow, filaments of gas too thin to see, galaxies buried behind veils that only infrared light can penetrate. And yet, for a technological species on a small planet around a very average star, the universe has left just enough clues. Red-shifted light, subtle distortions from gravity, tiny temperature ripples in the cosmic microwave background. From those, scientists reconstruct 13.8 billion years of history. Before we get started on the next layer of that reconstruction, think about what this resembles. Voyager reached the edge of the solar wind and discovered that the heliosphere's boundary was stranger, more dynamic, more structured than anyone predicted. JWST is doing the same thing at the edge of time. The boundary between no galaxies and the first galaxies is not clean. It is messy, foamy, alive with unexpected objects. Home, in both cases, turns out to be embedded in a larger, more active environment than absolutely no one anticipates. The solar system is not an island in calm water, it is surfing an interstellar wind. The Milky Way is not an isolated city, it is one node in a vast, hidden cosmic web. And you are not merely in the universe, you are a direct product of that web, of that hidden layer JWST is finally bringing into view. If JWST can turn the invisible scaffolding of the universe into something you can almost picture, the obvious question is, what comes after that? How do you peel back a layer beneath the hidden layer? Tonight, we're going to look past Webb itself, into the next generation of eyes the solar system is about to open on the cosmos. The first is already on the calendar. The Nancy Grace Roman Space Telescope is often called Hubble's wide field cousin, but that undersells it. Roman will stare at the sky with Hubble like sharpness, yet cover areas hundreds of times larger in a single shot. Where JWST zooms in on a tiny patch and reveals impossible early galaxies, Roman will sweep huge regions and turn those discoveries into statistics. How common those galaxies are, how they cluster, how their distribution traces the invisible dark matter web. This is expectation versus reality at cosmic scale. The expectation is that Roman simply fills in a census. The reality is that with its enormous surveys and precise measurements of gravitational lensing, it will map the dark filaments that JWST only hints at, turning distorted galaxy shapes into a three-dimensional chart of where the mass actually is. By the end of tonight, you're going to understand that Webb is not the end of the story. It is the prelude to a network of missions. On the ground, the extremely large telescope in Chile and its cousins are preparing to do something equally dramatic. A 39-meter mirror, adaptive optics that cancel Earth's atmospheric blur, and instruments tuned to the faintest smears of light will let scientists dissect individual lensed galaxies JWST finds. Where JWST sees an arc, the ELT will resolve internal structure, rotating disks, clumps of star formation, perhaps even signatures of mergers in those first few 100 million years. These observatories do not compete with JWST, they interlock with it. Spacecraft like Webb and Roman give clean, stable views across wide wavelength ranges. Giant ground telescopes add raw collecting area and ultra-fine detail. Together, they push the boundary of what can be measured about those early planets of data points in the cosmic web. Then there are the missions that reach into wavelengths Webb cannot touch. Proposed far, infrared space telescopes and next generation X-ray observatories would probe the coldest dust clouds and the hottest, most violent regions around black holes. They would see forming galaxies wrapped in so much dust that even JWST's infrared vision misses most of their light, and they would track how energetic winds from black holes sculpt that hidden structure. No one expects all of these missions to simply confirm the current picture. No one predicts the dark matter map will line up perfectly with theory, and absolutely no one anticipates that the count of galaxies or the pace at which structure grows will remain unchallenged once this fleet is flying. That is the deeper pattern. Each time a new observatory turns on, hidden moves. What was invisible becomes routine, and a new, stranger layer appears underneath. The real question is not whether we have found the universe's final structure. The real question is what the next layer will force us to rewrite. So take one breath and run back through tonight's universe. We opened with a number so huge it feels almost fictional. 2 trillion galaxies in the observable cosmos, a census stitched together from Hubble's deepest images and models of all the ultra-faint systems it could not see. That was supposed to be the map. Then a new spacecraft turned on and the map began to warp. Tonight, we're going to remember that pivot. JWST stares into the same dark, empty-looking space and finds galaxies that are brighter, more massive, and far more common in the first few 100 million years than scientists predicted. Expectation? A simple, slowly brightening dawn. Reality? A skyline. Massive, compact galaxies blazing when the universe is still a cosmic infant, like finding skyscrapers already standing in what should be a Stone Age village. No one expects those systems in standard simulations. No one predicts that when you push deeper, some of the early Hubble-based 2 trillion extrapolations may actually shrink, because the ultra-faint population does not rise as steeply as the models assumed. And absolutely no one anticipates that the real headline will not be more or fewer galaxies, but stranger galaxies, living on a hidden scaffolding that theory drew in pencil long before the images arrived. By the end of tonight, you're going to understand that scaffolding as the quiet main character. Dark matter, cold and invisible, sets the cosmic boundary lines, carving out a web of filaments and nodes where gas can fall, cool, and ignite into stars. JWST's massive early galaxies press hard on that framework, testing how fast structure can grow, how efficiently gas can turn into stars, and whether the standard Lambda CDM recipe really captures the universe's first frantic billion years. Layered on top of that is the dust. Hubble saw the clean, unobscured side of the story. JWST's infrared vision cuts through the grime and reveals a buried population, star-forming galaxies wrapped in their own smoke, invisible in optical light, suddenly obvious once the wavelengths shift. Expectation? A transparent early cosmos. Reality? A universe already hazy, already busy, already hiding its work. These discoveries are not just pretty pictures. They are stress tests. Each bright, overachieving galaxy forces simulations to sharpen. Each dust-obscured system demands new models of how quickly stars enrich and pollute their surroundings. Together, they threaten to rewrite how dark matter gathers, how the first solar systems form, and how cosmic history accelerates from smooth plasma to a universe packed with planets. Now, let's begin to fold that back into your own sky. When you walk outside tonight and look up, you're not just seeing stars, you are seeing the luminous frosting on top of a structure mostly hidden. Ultra-faint galaxies below current detection, dark matter filaments with no direct glow, and entire families of worlds veiled in dust. The visible cosmos becomes a surface, not a full volume. The next time you notice that thin spray of starlight, remember, most of the story is still beneath it, in a layer we have only just started to uncover. That thin spray of starlight above you tonight is no longer just a backdrop. It is a question. Every point of light is a hint that there is a hidden layer beneath the visible surface, a deeper structure that the James Webb Space Telescope is only beginning to reveal. So the next time you step outside and look up, do not see a flat ceiling of stars, see a cross-section through the cosmic web. Behind the bright planets and the familiar constellations, imagine ultra-faint galaxies dissolving into the dark matter filaments with no glow at all, and entire systems buried in dust that only infrared eyes can penetrate. Tonight, we're going to let that mental image follow you out of the video and into the real sky above your head, because this is where you come in. Cosmology is no longer a closed book with a neat answer like 2 trillion galaxies written on the last page. With every new JWST deep field, scientists are being forced to redraw the table of contents. Some early results say there are fewer ultra-faint galaxies than Hubble-based models predicted. Other measurements show massive, bright galaxies appearing only a few 100 million years after the Big Bang, far earlier than the standard timeline allows. So, what do you think JWST is really telling us? Does Lambda CDM just need a tune up at the edges, a few parameters nudged so that the solar wind of data and the theory line up again? Or are we discovering that the universe has always been this wild with dense clumps, fast, forming structures, and a hidden layer of complexity that absolutely no one anticipates until the instruments finally reach far enough? Sleep well tonight, and tomorrow we will continue to explore the deepest mysteries of the cosmos together.